Start screen share.
Sure. Do you want us to present like slides or the
Yeah,
report
yeah, of
itself?
course. Slides itself.
So,
Slides,
okay.
slides.
So we have the slides from a presentation which we did for the seminar, and we have just extended to project a bit. So I'm just quickly
No,
share
but
the slides
then
on.
you don't have the slides. Nothing more than the seminar.
No, actually, we have not prepared slides for that. But like our experiments are like detailed in the report.
Okay, then run us just immediately flash the slides and then move to the report.
Yeah. Okay. You can see my screen.
Yeah, yeah, yeah.
Okay. Okay. Uh, right. So we were basically working on extending this paper, like actually experimenting with some parts of this paper. So this is like a human AI teams, and what we did was basically it was to enable humans to collaborate with AI, and basically we want the human to choose when they want to rely on the AI or ignore the AI or collaborate with the AI, and this was to be done in a task by task basis. Um, just 15 minutes. So related work I'm not doing that actually. Yeah.
Skip
So
related work.
yeah. So we basically say that the human has to make the decision why, and you have some input X. Basically, it can be images and text or whatever be the task. And we basically model the human as a set of parameters which are unknown. Um, and we have given an input X, right? So, and the human decision will be final after taking. Yeah, they'll take the AI advice, but whether they want to rely on that or not, it's their choice. So we are given a grounded decision y, and we are given a chosen decision by the human as y hat. So it's nothing but the loss function is a real number. And for I think our case we have used the 0 1 loss function. Uh, so yeah, if it agrees it's one, otherwise it's sorry. If it agrees it's zero, otherwise it's one. Um, and yeah, this is expression for the expected value. And yeah, so we basically want to learn this function R, which is like the main function. So what we do is that we first learn this integrator function R, so that for each data point and each AI decision, it tells us whether we need to ignore the AI or use the AI or collaborate with the AI. And then we will onboard the humans with the same AI system. So the first part is actually learning this optimal integrating function, and the second part is just teaching the Sorry about yeah. Second part is just teaching the human about this integrated function. Okay, so for our case, we have just used R from 0 to 1, and R is equal to 2 is left for future work, right? Um, so even in the project, we have not experimented with this R is equal to 2 part. We have
You're
used
saying
R is
first,
equal to 0.
first you learn the optimal integration functions. Next, what you do? Use
We
it.
onboard the human. We onboard the humans so that they can learn this integrator function. Like when do they need to listen to the AI and when do they need to ignore? And like we are basically learning regions in the embedding space. Is that for each region you have this label as 0 or 1,
Mhm.
right? Okay.
Okay.
Um. Yeah. So this is sort of the framework. So this is a given input, and then you have AI agent making a decision, and then you are basically using it to integrate, and you get the loss. Um, so there are two problems. One is how do we find the optimal integrator, and how do we ensure that the humans follow the optimal function. So in our project, we are just experimenting with the first problem because the second problem required like an LLM access, and we didn't have a free API key, so we have not demonstrated effectiveness on the second issue. But yeah, the first problem is just like the region discovery algorithm, which is discovering regions in the embedding space. Okay, so some of the basic sanity checks was that it should be easily understandable. Like the humans need to have an intuition as to which regions do they need to listen to the AI. So that means that it should each region should be like localized in space, and you should have an indicator function for each region, whether or not you sort of like whether each point belongs to a region or not. And you also have a textual description, which will make it easily understandable. And for each region, you have this integrated decision as well. After that, we are basically maximizing the performance gain of the human. So yeah, you basically start
Did
with
you
the
solve
prior
both
function.
problems? Did you
Pardon?
use both? You use both properties
Which one? This?
in the project. You incorporated both properties, right?
Yeah. So this is part of the code base itself. Yeah. So all of these properties have been implemented. So we want to maximize the performance gain such that this is the loss given by a prior integrator function. So this prior integrator function is the prior the priors that the humans have before they have been introduced to the AI. And this R hat is like the current integrator function that we have. So we want to maximize this loss, which means that we need to minimize this loss. So in the project, what we have done is we have experimented with different priors, and we observe how that is changing the performance, like how that is affecting performance. And by performance, we have defined like 2 3 metrics. So yeah, like I'll come to that. Um, right. So we have been given a data set XY, the decision and the integrated decision. Uh, so yeah, that is, we'll just skip through that. Uh, uh, and then we have the representation space given by inputs X, and it's a cross-model space. So you also have one embedding dimension of natural language. So yeah, it's basically yeah, this is the embedding space E cross A, where E is the embedding space from the input X, and A is say the action, and one mode of X is natural language. And each region is defined by like a centroid point CK, and it has neighborhood around it with an integration label, RK, and it has a radius and also has a scaling vector. So the indicator function of each region is given by this formula, which is like identity like 0 1, and the condition is this. Okay, so it should lie within this radius gamma k. Um, so yeah, so the region, the constraint is that like for each region, there should be they should have a minimum number of like minimum fraction of the total data, such as beta L. So the minimum region size is defined, and the maximum region size is also defined by beta U, and like at least a fraction of points alpha should have the same value as Ri star, and there should be a performance gain of at least delta. So yeah, this is the constraints that we have. And after, so for each round, in each round of training, we are discovering a new region, and we are adding that to the set of regions. And after all the T rounds have been done, we are basically making the decision as such. So if the point does not belong to any region, you just take the prior function. And if it does belong to one region or multiple regions, we are taking a majority vote over all the regions that it belongs to. Okay. Right. And in round K, like the performance gain for each decision can be given by this. Okay, so this is like yeah, this is like R is like uh, the decision that we are making, and this is the loss function. So this is the loss function from the previous prior that we had, like the previous region prior that we had. So K minus 1th round. Um, yeah, and like to make the optimization problem differentiable, there's a multiplier lambda, and there is a constant C1. So for differentiability, actually, you just need like C1, but we have like there is a lambda in the paper just in case. So yeah, this is like the final optimization function that you have. And yeah, it is, yeah, it's basically all these terms. So in the first term, I think you're maximizing your performance gain. In the second term, you want you want like a you want at least alpha fraction of points to like alpha fraction of points to agree with your decision, which is the optimal thing. And this is like the lower upper bound, and this is the lower bound on the number of points that should be in a region. Okay, and this is sort of the algorithm. It's not really necessary in a project right
Can
now.
you just recall the each of the components of objective? The first one.
Yeah, this one is maximizing the performance gain. So since we're taking a max over all the hyperparameters, we want to maximize this term, and this is basically so if you recall, this alpha is from this part. So at least a fraction of points must have the same value of Ri star. Okay, um, so this is like a consistency check. So it's like your region is not deviating too much, and So this is that term, and this term basically says that beta u states the upper bound of the region. So there should be like the maximum number of data points that you can have in a region is given by beta u, and beta l gives you the minimum fraction of data points that you need to have in a region. Is this clear?
Yeah.
Yeah. Okay. So this is the algorithm that we're using. So we assume that you need to find t regions, and so we run the loop for one to two t. So in case like in between there is we don't find a region or it doesn't match the constraints, and we just skip that region and we go on. So this is the reason for doing one to two t, and then yeah. So you have for each so you have two decisions for each region. You can either keep that R value to be 0 or 1. And for each, you are computing a gain vector, like the performance gain. And you are also initializing like all your parameters, region parameters, which is C0, gamma 0, and W0, which is like the centroid, the radius, and the scaling vector. And then you just like do this. You do the optimization over like these three parameters to gain the optimal parameters for each R, and then you have like the candidate region for each R, parameterized by these three parameters and actually four parameters because of R. Um, and yeah, and then you basically see if that the performance gain is greater than delta, you will add that region or not. So yeah, this is sort of the flow of the algorithm, right? And region description, I'm not going through because it's not relevant to the project right now.
Okay,
So
can we
yeah,
get to your yeah, can we get to your
yeah, yeah,
implementation and
yeah. I'll
that's all.
just
This may be the right time to branch
yeah,
off. Yeah.
yeah. Okay. So apologies for not making the slides for this. But I'll just go over what we're doing. So yeah, we basically want to like we basically want to experiment with the priors that we have, and we want to sort of perform like measure two things. One is like can we like can we make um, can we make the region discovery algorithm predict like discover different classes as regions, okay, and how much like basically does it act as a clustering algorithm? So in one region I only have images from one class, and from other region I just have images of a second class, and so on. And how much mixing do we observe in each of these regions? Like how many number of like unique classes are there in the region, and so on. So if a region has four different classes, then it
So
probably doesn't
this is what HRO is about, right? This is about RO.
uh sorry, could you
You in the project you experimented with different priors RO, right?
yeah.
That is the first point.
uh yeah so yeah, I'll just explain what we've done. So this is, yeah, we are basically measuring the performance, and we are seeing if it is able to approximate like different classes. So if each region can correspond to a different class. So I'll just give you some details about the data set. So the data set is the image net. So this is like sort of a subsample of the original ImageNet data, and it has like 4,000 images almost, and there are 10 unique classes given by these. So there's a cassette player, there's a garbage truck. So the all of these are pretty all of these are pretty different, so to speak. So none of them are like very close to each other or something, and like each of the class has approximately the same amount of images. So it is a balanced data set. Um, and what we're doing is that we are using ResNet 18 for the experiments, and it is pre-trained on the ImageNet dataset, right? And yeah, so this is a good way to showcase the region discovery algorithm because the AI model accuracy is very variable. So the overall accuracy is about 0.58, but the class-wise accuracy, as you can see, is given by this. So for some regions, you have like 0.94, 0.8, and so on. But for some classes, you have like 0.08 and like very low accuracy. So ideally, for these classes, you would expect to see like the algorithm telling you not to trust the AI and just like yeah, let the human make the decisions. You can hear me, right? Hello.
So where
Yeah.
are you prompting the humans to make decisions and not use AI? Which part?
Yeah. Uh, Wait. Like you're basically asking where we are getting the data for the human decisions.
No, who's prompting that the human should make decisions and not AI?
So that is
So
given by
that
the integrator function, right? If
Yeah.
the
So
integrator functions,
where have
yeah.
you invoked it? You're invoking it here.
Yeah, we will invoke it. So if the integrator function for a particular region is given to be one, then we will trust the AI decision. And if it's if it's zero, then we are not trusting the AI decision. We are letting the human make the decision. And we are assuming that if the human is making the decision, the human accuracy will be about 0.5, which is on the lower end
If the
because
integrator function gives output 0, then go by human decision, right?
yes. And we are assuming that the humans have an accuracy of 0.5, which is on the lower end because these set of images are pretty, yeah, a human might be able to do better than 50%, but that is like a baseline that we're assuming, the worst case
And
scenario.
at least accuracy of at least 0.5, right?
Yeah, yeah, like that is a random, yeah. Uh, is that clear then?
Yeah.
Okay.
So for the
So,
optimization problem, will you also take into account the number of times human had to interfere?
uh, what do you mean by the number of times the human had to interfere? I'm sorry.
Like number of times the AI function was not sure about the marking the region or something like that.
So if the AI, so if the integrator function is zero, then the human has to interfere, sort of, right? Like at least that's what our assumption is. Like at least that's the integrator function that we're trying to learn in the discovery algorithm. So the number of times means that basically the number of regions which have R is equal to zero, right? If I understand you correctly.
Okay.
Uh, okay. Um, right. So these are the accuracies by the AI model, and we have like 512 dimension vectors, and this is generated by the ResNet. And just to give a glimpse of the data quality, like if we project these embeddings to the TSNE space, then you can see like that is a clear sort of clustering amongst these images. So yeah, they are not like the data quality as such is not bad because like even in the sample you can see that like they're pretty discernible. So it's natural that you would get some clusters, but still the AI accuracy for like the French horn or the English spaniel, which is like a dog, so that is like very low. So it is like a good data set to test this model on because you have variable AI decisions, but you have a good data set. So the human might be able to make good decisions, right? So the first analysis that we do is basically we measure the performance from different priors. So the question we are trying to answer here is does the prior chosen affect the performance of the region discovery algorithm? So whatever beliefs that the human might have, does that
Can you
affect
show
our
DC plot? Can you just show DC plot? Yeah,
pardon?
just scroll. Bas. See, so you're saying that this is you're saying the AI algorithm is actually capable. It has capacity to discern.
Yeah, like these are generated from the embeddings of the AI model. So yeah, but it's
Yeah.
still showing bad accuracy for some of the classes, which means that there is separability in the images, but uh, like during prediction or inference, AI models is not able to get there.
Yeah. So that is those blue, light blue. You're saying those
Yeah,
are the ones mixed up, right?
yeah, like there is like yeah, this region is very um, it's
Okay,
hard
fine.
to yeah. So yeah, we want to basically change the prior function that we're using, and we're basically seeing if there is a like yeah, does that affect our region discovery algorithm performance? So the four priors that we're introducing is these four. Oh, yeah. So one is an all zero prior. So what we are assuming here is that the AI decision is completely trusted. I know that zero corresponds to us ignoring the AI, But as a prior function, like 0 is that we're trusting the AI. And for like for all data points, we're assuming that the AI decision, like we have to, um, yeah, we have to take the AI decision as is for all, yeah.
Okay.
And all ones is basically like they're not to be trusted. And for all these data points, we assume that the AI decision is wrong, other than those regions that it's discovering where it's saying that we should trust the AI here, and differ from our original prior, which is that the AI decision is not to be trusted. So these are the two like baseline priors that we can do. And the third prior is that a mixed prior. So we are assigning zeros and ones randomly to each data point with equal probability. So they're like half the data points have a prior of uh, 0 and the other half has 1. So for 0, again, these follow. So if the prior is 0, then they're trusted, and if it's 1, then it's not to be trusted. And yeah, so this is like a mixed prior. So this is like sort of a midpoint between the two. And then we also have a threshold based prior. So we noticed that like for all the classes which show an accuracy below 0.8, we assume that we are not trusting that AI, which means that we are taking the prior to be equal to 1. So we are taking the prior to be this. So yeah, for here, basically, except for these three, golf, ball, parachute, or tench, we are taking the prior to be 1. Otherwise, for these three, where the accuracy is above 0.8, we are telling that we can trust the AI, and yeah, you should just use the decision as is. Right. So yeah, how do we measure performance then? Uh, so we're basically saying that like one of them is the accuracy. So like from my regional discovery algorithm, I have my like integrating decisions. So for each region, I'm getting either 0 or 1. And for that particular region, if I'm getting R is equal to 1, then I will trust the AI, and we'll just display the accuracy like of the predictions. So AI has some predictions already. So we'll just measure that accuracy. And if R is equal to 0 for a particular region, we are saying that we are not trusting the AI, and uh, the human has an accuracy of 0.5, right? So the human is able to predict the images like 50% of the times correct, right? So that is how we are measuring accuracy. And for the logistic loss, like I'll just illustrate with two scenarios. So if we want if we want to trust the AI, which is R is equal to 1, and the accuracy of the AI model for the particular region, like for all the data points in the particular region is very high, then we are basically saying that good it's a good match. And if it's 0 and the AI model accuracy is very low for that region, then that's also desirable. So we are sort of modeling it in terms of a logistic loss sort of problem. So if R is 1, then if this A is high, then that's a desirable thing because that will minimize the log logistic loss. So yeah, these are the two measures that we're using as a performance, and so this is sort of not given in the like these are not given in the original paper. So this we've just made like we've come up with our own. Uh, yeah. So as I said, we assume that the human is right 50% of the time, and yeah. So we are basically seeing that the all zeros prior is better than all the other priors, like in both accuracy and the logistic loss. Like it is giving us the highest accuracy, which is followed by this mixed prior. And we see that the all ones and the thresholding prior is sort of the same performance, right? Um, so yeah, and just to clarify, the baseline accuracy was around 0.5, 58. Right. So that is the baseline accuracy of the AI model if you are using the AI model as is. So we are seeing a
So
improved
all
performance.
of these are better than the baseline.
Yeah, yeah.
Okay.
I mean, the threshold is almost the same. But yeah, other than that, we are getting better performance than if you're just using the AI model blindly. And this is like a proof of concept of the paper, sort of. Like it's basically giving you better accuracy. And this is if you're assuming that the human is like 50% of the time, which is also sort of very low for a given data set. But yeah, at least like if you have a very dumb person, then maybe 50% is a good metric. Anyway, so yeah, so the all zeros prior is outperforming all the other prior functions. So in the all zeros, we are basically assuming that if you recall that the AI decision is to be completely trusted. Like then it is aiming to find regions where the AI decision is very bad, like the AI accuracy is very bad. So this is one of those regions for the all zero prior. So you can see that these are the images of the dogs. If you recall, this has an accuracy of 0.08, which means that it is successfully being able to like find regions of low accuracy such that it can set the integrator function there to be equal to 0, right? Because there we are basically saying that do not trust the AI and just use your own decision. And similarly for the all ones prior, we would expect that the AI model should like the discovery algorithm should basically find regions where the AI model is good, and that is like this is one of the regions, and this is like images of parachute. If you recall, that had an accuracy of 0.8. So yeah, it is sort of trying to find regions where the AI model is good, and we should trust the decisions there against the prior, which is like do not trust the AI at all. So yeah, this is sort of the first analysis that we've done. So yeah, we're basically showing that there is some proof of concept that it's working and it's able to discover regions where the accuracy is very like uh, yeah, it's low or high depending on the prior. So the second analysis that we're doing is basically a relation between regions and classes.
Only
So
4 minutes left, huh? Only four
yeah,
minutes
yeah,
left.
yeah. So we're basically seeing if regions can be associated with different classes. And here we use two metrics. So the number of unique classes present in each region and the fraction of the majority class in the particular region. So again, if you see this table, this is given by this the pair values, which is the number of distinct classes and the fraction of majority. So in this, you see that again, the all zero prior is doing better than all the other priors. The thresholding is doing very bad because number of unique classes is 4 and the majority is also very less. So yeah, the basic takeaway is that the all zero prior is doing very good, and it's able to actually approximate like it's able to make the discovery algorithm a clustering algorithm of sorts. Like it can basically approximate classes. But what we also saw was that for a particular class, there might be subdivision of the images. So like this is from one of the regions and this is from outside that region. So in this the left side you see that the churches are very like it's a proper picture of a church outside and it's not very far or it's not inside a church and so on. Um, but on the right you see like different close-up images of churches like this one, and you see that there are insides of churches. So this region it's not able to predict the like it's not able to predict the church very well, but on the left side it's able to predict. So there are subdivision of like classes amongst the region, like amongst a particular class for a particular region. So yeah, this is pretty much it. And we are basically what we wanted to also do was incorporate R is equal to 2 and come up with some sort of data set subset selection using the Decile library that you have mentioned in class to sort of see if we can pick a subset for which the discovery algorithm does better. So yeah, that is.
Were you able to do that? Sorry, just go back. So
No, no, for the Decile thing, we are not able to figure out the code. Like it was like actually for the quads library, it was taking PyTorch, like it was as a PyTorch data loader and so on. So, but for our data set, there was no training involved with ML model, so we are not able to figure out in time.
I don't understand. If it's using a PyTorch data loader, what is the problem using it?
Uh, so like we were not training a particular data model. Like we're not training a particular ML model. We're just sort of doing a region discovery algorithm which did not use Torch or any like similar library. Like it is just simple NumPy. So we're not able to like uh, make the two code bases compatible in time. But yeah, this is something which seemed interesting as well.
I still don't understand. We could explore better selection of good subsets. This is certainly a very low hanging, but nobody has reported. I mean, I'm not understanding. What is the problem for you to use PyTorch data loader
Uh,
that CORDS requires?
We are not sure if it's like actually we didn't understand how it's doing the dataset subset selection. Like even if we like
No, or is it that you couldn't spend sufficient time because there's another team, I mean, a couple of teams that have been able to do it. You could have asked question, no questions came from you, right? Vishak, do you anticipate any problem they faced? No.
No, sir.
Hello. Can I stop sharing my screen?
Yeah. So, can you show the code?
Yeah. Yeah. Sure.
Who's going to present next text? Sharp. So both of you have done equal work, is it, in this project?
Yeah, like working on the analysis.
Okay.
The two
And
analysis.
are you guys interested in taking this work to the next level by, say, publication? Because you have some interesting results which you could have used chords. That
Yeah.
means.
Yeah. Actually, that is something that we wanted to do, and also the R is equal to 2 part. So this we are not able to figure out because that might have required some like using some more optimization and all of that. But yeah, we couldn't find the time to do that.
Okay. So you are interested in R equal to and
Yeah.
and
Using
improvisation
the decile and the chords.
using chords. So Vishak, do you want to comment on anything here?
Nothing much.
Because you have positive results. Is that if you had reached out, we could have held better. That's all I can say.
How does your result compare to the state of the
Pardon?
state of the
No, actually, they just verified what is coming, what has been presented. I mean, some sense they re-implemented and verified. So, is it that I think the related work came in their seminar, and I'm assuming that you're banking upon
Yeah,
their
this
improvement
is
based
yeah.
on your seminar itself, seminar in the related work section of the previous paper that you verified.
Yeah. Also, like this is pretty recent paper, so and like not some work has been done, but that was like in 2020 and 2021. But yeah, this is the most recent paper I think for this particular problem, and this was in I think near of 2023. So yeah, after that, I'm not sure if further work has been published because for citations, I think there were not many. I think one or two only. But yeah. Yeah, you wanted to see the code, right? Is it like, are we out of time?
Go ahead, go ahead. And show until the next team joins. Vishak,
Okay.
can you just follow with the next team? Meantime, I'll just have a look at the code. Vishak, can you just follow
I
with the
think
next
the next team just joined and I think they left because this meeting is still running.
No. Well, just ask them to join.
Yeah.
Just ping them. What is their name?
Ayush something.
Ayush Singh, is it? Just ask Ayush Singh. Just ask them to join, please. They should join. Yeah, go ahead and show the code.
Yeah. So yeah, you can see that like for some of the regions in the middle, you're getting null values. So basically, in these sort of rounds, it couldn't find a good reason, and it just moved on to the next round until it could. So yeah, that's it, one of the implementation things. And yeah, this is like one of the regions. I think for the all zeros prior, where you're trusting the AI, and we are trying to find regions where the accuracy is low. Yeah.
Yeah, Ayush, please be here.
Yeah, yeah, do this. Okay.
Yeah.
Okay, then fine. Then I think we'll move on to the next presentation.
Okay.
So one of the students will be in touch with you, but please take this work ahead.
Okay. Yeah. Sure.
Thanks. Ayush, can you get started?
Hello.
Yeah, please present.
Yeah, we both have joined from this laptop only.
Yeah, please present.
Yeah.
I can't see your screen.
Is it visible now?
Yeah, it's visible.
Yeah, so this is our report. So, yeah, our project is based on comparing optimizers, different optimizers for image classification tasks. And for this, we have compared two new optimizers, Sophia and Lion, with the conventional ADAM and SGD optimizers. So, the major highlight of these two optimizers are that line optimizer is a first order optimizer, and like basically it has uh, it has only it has same update in each step, and it's developed by Google, and it's a fast optimizer. And Sophia is a second order optimizer with uh, in which the step size also varies. So due to this, it's also like computationally heavy.
Actually, you don't have slides, is it?
No, sir.
Okay, I was actually, so this is, actually I'm a little lost. Can you again present? Is this building on your, is this building on
So
your,
yeah, this was
on your
just
seminar?
so this was just like the introduction of these two optimizers.
Which two optimizers? Sorry, I was looking at your seminar. This is not connected to your seminar, is it? Is it? Can you
Sorry.
just go to the top again, the title? So comparing optimizer with image classification. Okay. So this is Ayush, Ayush
Yeah.
Munjal and Bhavishya. Okay, okay. Not Ayush Singh Badoria. He's not part of it.
No.
So what was your seminar topic?
The paper presentation.
Mm-hmm.
That was like Adam why the Adam optimizer converges faster than STD optimizer.
Why the item was optimizer converges faster than HDD optimizer?
Yes.
I see. So this is not related to that.
No.
Okay.
Okay. So we will compare these four optimizers on for image classification task on this CFAT dataset, and we will measure the performance based on the learning rate for like changing the learning
Which
rate.
four algorithms? Which four algorithms?
SGD, Adam, Lion, and Sophia optimizers.
Okay.
And with respect to batch size and finally, with respect to time taken for the convergence. So we use a very basic CNN
SGD, Lion, Sophia, and
Adam.
okay,
Adam
and
optimizer.
I see. And then you look. So this is um, just exploratory. You're just exploring. I mean, there's no hypothesis. There's no end goal you have in mind, is it?
Yeah, this is just like experimental kind of
Okay.
analysis.
Okay.
So yeah, so first we have this result for accuracy versus learning rate for different for these 4 optimizers. So we can see that Lion and Sophia outperform the other two, and they are almost comparable, Lion and Sophia. And so, like for a given learning rate, Lion and Sophia generally give better up to a point, and after that, STD gives better. But the best performance for any learning rate, we get it from Lion and Sophia. And for batch size, again, we have similar observations that Lion outperforms the other 3 by a good margin. So again, like the best accuracy for any batch size, highest accuracy we get from Lion optimizer only. And finally, we test for the training time, and on this C10 dataset for a fixed learning rate and batch size. So batch size of one, so yeah, over 10 epochs and batch size of 512. And we did it over like Google Colab GPU. So for training time, the results were almost similar for all 4 optimizers. So like for Atom, it was slightly higher, but uh, like not much uh, difference than other 3 optimizers. So yeah, so taking into account these 3 uh, results for these 4 optimizers, we can conclude that Sophia and Lion, like they give better accuracy than SGD and Adam. But yeah, and almost they have the same computation uh, capacity, so almost same comparable training time to Sophia and to Atom and SGD. So yeah, so these new optimizers are like very uh, like very comparable to the currently used popular optimizers.
So Ayush, in the Sophia and Lion paper itself, these comparisons would have been made, right? With
Sorry,
Adam, with SGD.
sorry.
The Sophia and Lion papers, this comparison would have already been made, right? They would have already compared with Adam and SGD.
Yeah,
Yeah,
so
I
like
mean, yeah, just wondering what I think the question is, what is your additional insight? This would have been already done in that paper. And you have not explained also what is, you have not two questions. You have not explained what Lion and Sophia do. So you just started with Lion and Sophia. What do Lion and Sophia do? And second is, yes, if Lion and Sophia were whichever is the latest would have compared against the others, right? Vishak. So that's what you were asking, right, Vishak?
Yes, sir.
uh, yeah, so Yeah, so in the paper, like they would have compared that, but like we wanted to do like the comparison of these new optimizers to study like how uh, like how much better than they perform these with compare comparison to these conventional HCD and Atom. And yeah, and for like the explanation of an Lion and Sophia. So like Sophia is a second order. So being second order, it's not much used because of heavy uh, computational capacity and computational resource, and it's like it's based on using Hessian diagonal. And yeah, so and for Lion, it's not a second order, it's a first order optimizer only. And yeah, so like, and because of that, it doesn't have that much computational requirements.
So what Lion uses? You're saying Lion is a second order optimizer. Is that what you say?
Sorry?
Lion is a second order optimizer, right?
No, Sophia is a second order optimizer, Lion is a first order optimizer.
So what does Lion do? Is Sophia Gaussian gradient?
Sorry?
Is Sophia Gaussian gradient based method?
Yeah, so Sophia is a second order based on Hessian matrix, and Lion is first order based on uh, like based on its like the main highlight is that it doesn't it is not adaptive like Atom, and so that was the main motivation behind this optimizer. So it is a very memory efficient optimizer.
With Sophia.
So Lion is a first order optimizer which is not adaptive, and due to which it is very memory efficient as it keeps track of only the momentum. While Sophia, it is a second order optimizer which is like which requires very high computational power. So it is not as much memory efficient as Lion, but it is slightly more accurate because of this second order uh, optimizer.
I see.
Yeah.
Ayush, do you have any extension of this plan? Like you didn't get time to do that extension or something like that?
Yeah, because you just studied and actually I'm not even so extension in the sense you have not first of all not even reported what that paper does, right? See, one of the previous teams, what they did is okay, they reproduced some numbers, they verified what the paper is presenting. We have no idea what. So I'm assuming Lion is the latest of the lot. Is that correct?
Yeah, like both are in 2023.
So if Lion is the latest of the lot,
Yeah. Yeah.
Hello. Yeah, so this is Bhavishya. I don't know if it makes a difference. Actually, I've been sick for last month, whole last month. So, and one of our project, one of our member dropped the course. So, we got lesser time than others to work on this project. And I don't know if it makes difference, but yeah, I thought I should tell you that.
acha, so Bhavishya was there. Bhavishya contributed. Bhavishya is not even there in the meeting.
Yeah, we have joined from the same laptop only. One laptop.
Acha. Okay. So you're saying Ayush was sick for the entire last month, and one of your other members left, right?
I'm Bhavishya, and I'm sick for last month. Yeah.
See, you could always have informed, no? See, you're just
Yeah,
telling.
I'll send you the reports or. Okay.
You mean the sick report, the pink slip?
I thought I could do it, but at the end, all the activities and the enzymes, it was harder for me to contribute as much as Ayush.
Acha. Okay. So you're saying Ayush did most of the work then?
Yeah, it was like 70-30.
Okay.
Yeah, we were planning to get more insights and find out challenges with Lion and Sophia at the end, but we couldn't proceed to that part of the project.
Yeah, like we were thinking of comparing these optimizers for other tasks also. That is like additional to image classification, like other tasks like regression task or uh, tasks like that also. But yeah, we didn't get much time.
So you could experiment only with one task.
Yeah, so for now we have done it for only one task, image classification.
But what did the original paper? Okay, can you just open the original paper? Let's say Lion is the most recent of that, right?
Yeah.
Because you could have at least gone into some details of Lion and Sophia. You're just verbally describing. See, even if you have less time, you can always make the best use of what you've read, what you understood, na Vishak? So you could have
Yes.
presented on Sophia, Lion. I mean, fine, those are new algorithms, and I would have then some insight. Insight is also lacking. You're just presenting results without any insight. Okay, can you
Yeah,
show
we
the
should
data?
have discussed more about these optimizers in detail.
Yeah, so I mean, just saying you're sick, and I can't buy that argument because even what you have done, you have not presented properly, right? You have not presented completely.
Yeah, we agree. Like we could have done the presentation better.
Uh, Ayush, can you go to the line paper?
Yeah.
To go down. So if you see the graphs, they have already compared with Adam on
Yeah, they have
multiple.
compared with Adam, and yeah, and for yeah, so like our main motivation was to compare Lion and Sophia because like these are the two new optimizers, and basically to use uh, Adam and SGD as kind of a baseline for comparing these two optimizers. So yeah, like we know that Lion and Sophia they would have been independently uh, like compared with Adam and SGD. So, but we wanted to compare Lion and Sophia together.
Okay, what is their finding? Ada factor Lion. Lion is the latest, is it? They have not compared against Sophia.
No, they have not compared with Sophia.
So is Sophia more recent then?
I think they are almost the same time, Sophia and
Yeah, they are same. Yes, they are actually almost in the same time period. Yeah, so Sophia is more latest.
So did Sophia compare against?
But like there is only 1 to 2 month gaps between these two, so I don't think they would have compared with Lion here also. Yes, here also they have compared with Adam only, not Lion.
So here, they have compared on GPT-2, etc. So Sophia
Yeah.
achieves. So now I'm a little confused further. See, you have said that Sophia is a second order optimizer, and Sophia, you're saying this is contradicting, right? You're saying Sophia is second order, but it's achieving a 2x speed up over Adam in pre-trained. How is it?
Yes, it is a second order optimizer, but so yeah, I think
Yeah, so you need to really be clear, na?
yes, we should have gone through these optimizers in more detail.
Okay. Yep. Anyways, have you updated your report? Just look at code. Choose your code.
Yeah, code, yes.
code is the same as Sophia and Lion's code, right?
Sorry?
Code is the same as Sophia and Lion's code, right?
Yeah, we have just used their implementation from the GitHub. So, like, here we have different functions for uh, these four optimizers: STD, Lion, Sophia, and Adam. And so this is the function to compare these optimizers for different learning rates. So so basically we just train all these optimizers on CFAT and dataset with this model. Uh, this is a very basic model. And yeah, so from this function we get uh, the results for different learning rates, and we have a similar function for different batch size. And yeah, from this different learning rate we also get the time for each optimizers. And I think like the reason the you are saying is that uh, Sophia converges 2 times faster. So like it's, I think due to its uh, like it's because like its performance is better, like uh, it's a better optimizer than Adam, so it's more accurate than Adam, so it which is the desired loss much faster than Adam. So Adam and Sophia like both are uh, second order, but because Sophia has uh, better like the better update step for the using the Hessian matrix. So I think that's the reason why it converges 2 times faster than Adam.
Talk about Sophia, right?
Yes.
Okay. Okay, then can we move on to the next presentation? Thanks. Prayas, can you get started?
Yeah. Thank you. Sir.
Yeah, good afternoon, sir. Am I audible?
Yeah, you are audible.
1 second.
Where are your teammates? There.
Alone.
Hello.
Yeah, I am alone.
Okay.
You are alone, Prayas?
Yeah.
Yeah, go ahead and present.
Can you see my screen?
Yes.
Uh, how do I minimize this? Can you still see my screen? Hello?
Yeah, I can see you.
Yes, yes,
Oh,
yes.
okay.
I think this is maybe of immediate relevance to this topic, Vishak. So I'll kind of upfront tell you should follow up on this topic, right?
Yeah, this is also my MTech seminar, so I'm very
Yeah.
excited to.
Oh, you're working with whom?
Soman Chakrabarti.
Okay. Very good.
So RAG is the problem, but submodularity I tried to see because of this course. So
Okay.
the RAG problem is you have a LLM and you retrieve it with a retriever component so that you make up for the lack of knowledge in the LLM, and also retraining it to update the LLM might be expensive, so you augment it with a retrieval component, so it's you mitigate, you step away from the cost of retraining. So that's the RAG problem. Now, usually the retrieval corpus is huge, and my aim is to see what's the role that submodular optimization can play in the retrieval ranker. So I will go ahead. I will tell what that means. So since the corpus is large, I opt for a re-ranking approach. So let me first show the pipeline. So re-ranking approach means you have a corpus. The first stage re-ranking will be dense retriever, and I will first retrieve 50 documents. Now I will do BM25 over this. I will retrieve 20 documents. And now finally over this, I will apply submodular. So I won't apply submodular over this whole corpus. I will apply a submodular on this 20 documents to finally retrieve the 5 documents. Now there's a very interesting primal dual relationship, and this is not standard terminology. So the standard terminology for dual problem is long context learning. So the primal formulation of the problem is you have a LLM, and you augment a retriever on top of it. So you have a corpus. The retriever will find the documents, suppose top 5 documents, and it will give it to the LLM. So it usually has a dedicated retriever, not necessary, but usually it has a dedicated retriever. The dual of the problem is very interesting. So LLM, you give the entire corpus to it, and the LLM will decide what to do with it. Entire corpus, or you give a fraction of it. So LLM will decide what to do with it. So this is the dual formulation, and this commonly falls under long context learning. Again, I would like to emphasize this primal dual is just my terms. These are not standard terms. So related work, Realm. This is the progenitor of the field where it all began. So Realm paper, one of the first papers implement RAG. Now this RAG, so this is the method name. It confusingly matches with the topic, but this is the paper name, and it improves upon Realm. Now the dual formulation, Unlimiformer is one of the paper which solves the problem as dual. Again, it does not term it as dual, but it's actually solving the dual problem. Now for submodel optimization, this paper, very popular paper on document summarization. Now, surprisingly, there is no work for submodel optimization in the RAG settings, which might be due to that the RAG is a very new field. So, but as the case stands, this there's no work on submodel optimization in the RAG setting. The dataset I'm using this fever dataset. Now, what the data is, given a claim, you need to retrieve the evidence as well as find out if the evidence supports it, it's neutral or contradicts it. 200k train instances and 20k dev instances. Re-ranking approach, I have already went over that. Now the retriever and the NLI model. So retriever can be either sparse or dense. I've experimented with both. NLI model is dBeta base, the smallest model. The large model I could not try on Kaggle, it was giving out of memory. And the NLI model is fine-tuned on the train set. So submod function, what I've used is MI version of facility location, logdet, graph cut, all evaluated over sparse dense score. So what I mean by that is the similarity will be suppose it's like same DIDJ. Now the similarity can be either the dot product of the embedding, so that will be in the dense case, and in the sparse case, it will just be the BM25 score, BM25 similarity. So that's what I mean by that. Now evaluation over two custom-made functions as well. So I've defined what the functions I've made. Now if you notice that, so this is the first function that I made, query relevant similarity measure. So for the MI versions, it's sufficient to provide separate inter-document and cross-query document similarity measure. So DIDJ and QIDJ. But the facility location MI, it completely ignores one interaction, input set and query set. What I mean by that is you have the ground set, you have the input set, and you have the query. So facility location will consider this interaction, but will completely ignore this interaction. Facility location MI. Now that this is for facility location MI. Second one is second point is log.mi. This the second term controls the query relevance and
Can
how
you go
it
back to
does
the
is.
previous slide? Can you go back to the previous slide? So, yeah, you're saying the facility location considering only ground set, input set. Wait, no, input set.
So the objective is
Got it.
over.
Good. Yeah, that's okay. Go ahead.
So okay. Now the second term in the log.mi controls the query relevance. Now we have a single query, so this will some constant, and this is just the outer product. So this will roughly reduce, a term of this matrix will roughly reduce to this. This is the product of the query relevance, and this is the product of the document similarity. Now the query relevance is a difference here. Difference, it's reflected as a difference. Now another alternative, and in my, I'm sorry.
Yeah, go ahead.
So this is a difference. So in my opinion, a more natural alternative to express this query relevance would be instead with the product of the similarities. So this is what I do: directly model the document similarity matrix and include the query, not just the retrieved documents. So this probability, so the similarity matrix would be probability of DI given Q, DJ given Q, and the interdoc and the similarity these DI DJ similarity. And I just take the softmax and normalize it. So the probability is just modeled at the softmax of the similarities. So the similarity is weighted by query relevance with respect to the pair of documents. So the usual query is just DIDJ and with respect to only these two. Now this is a function of QDIDJ. So which is by the term query relevant similarity measure. Now this reflects the low score of a pair of documents which are highly similar but of little relevance to query. Earlier we won't be able to model that with a single matrix. Now we are able to model that. So observe that this observation neatly captures formulation neatly captures the input series interaction as well as the which is missing in the facility location MI variant. Therefore, we can directly apply this to FL and logdet without MI. The second function that I tried was sparse dense similarity. Now, usually what happens is sparse often outperforms dense similarity because the this downstream tasks usually have high correlation with the n-gram overlap, not the not the semantic overlap usually. But semantic signals are also useful. Sparse signals will only take us so far. So one very reasonable next step would be just to take a convex combination and control the sparse and dense probabilities. So this is the second formulation. Now the results.
Can you go back? Can you go back? Can you go back up? So the dense probability is sparse. What are dense and sparse probabilities?
As in the similarity scores. So similarity scores with respect to the dense function. So and similarity scores with respect to the sparse function.
So which are the sparse and dense functions? Sorry, I'm not understanding.
So sparse, sorry. So sparse function would be the BM25 retrievals, BM25 score, and dense would be just you have the retrieval model in the dot product of that embedding.
Okay, okay.
So BM25 will reflect the n-gram overlap score, and dense will reflect the semantic overlap score. Now results. So sparse ranking is greater than dense ranking. So sparse scores or for every variant is greater than dense scores. However, sparse and dense similarity together, which one has a positive effect over just sparse and just dense. So individually, sparse is performing better than dense, but sparse and dense is performing even better than sparse because our hypothesis was the dense signals were also useful. There's utility to them. So if you notice, there are improvements here over just the sparse.
Wait. Sorry, I missed it.
So dense variant.
Sorry. Can you present your results again?
So this is the screen. So dense scores for the dense variants of this for these three objectives: facility location, log data, and graph cut MI. These are the scores, right?
Sparse dense similarity has a positive effect over sparse retrieval, and this sparse retrieval ranking is better than dense ranking.
Sparse score. I'm sorry, this is typo. Sorry.
So Prayas, what is the Bartolard accuracy?
That is from a that is from another paper. That is just to compare with my model. I will come to that later.
Okay, sure.
Sir, should I continue?
So you're saying that the dense facility location so what does SD mean? SD means or sparse dense?
Sparse dense.
Sparse plus dense.
Prayas, one more doubt. How did you calculate the alpha value here?
I will come to that. That's an interesting part. I will come to that. Did I mention alpha? Okay. Yeah, sorry, sir. Go ahead. Sorry, sir. Go ahead, please.
SD graph cut MI. SD graph cut MI. That seems to be the best, right?
Yeah, like combination of both.
But graph cut MI again ignores the query, no?
But this sparse dense. But this similarity, it's in that what this in the query matrix itself. Or similarity matrix itself.
Okay, can you repeat once more?
So here in the this dense sparse cut MI. Oh, you mean to say with respect to the query? So query relevance. I did not check with that graph cut. The experiments were long. So I did not check with this query relevance with respect to the graph cut. Query relevance I respected with checked with respect to only facility location and log that.
So, so that is not clear to you. But the best performing is SD graph cut MI. Yeah, that seems to be.
Hmm.
Have you tried with multiple queries? I mean, have you tried with multiple?
Multiple meaning?
So this is just one instance, right? How stable is this? How reliable?
Yeah. So variance of this need to be checked, but it takes a bit more time. So the variance of this need to be checked. And also the sparse dense and query relevance. I haven't come to query relevance part yet, but these can be combined.
Okay.
So query
You're saying
relevance considers just
you can combine log.mi. You're saying you can compare log.mi with graph.mi. Is that the point you're making?
not MI, but the sparse dense measure and the query relevance measure, not the MI variant. I mean, if you want, you can. I mean, just have a proper SQ matrix, like for example, maybe identity and query SD, then DIDJ matrix. You already have this as the query relevant measure, so you can retrofit it, but it will more naturally fit in the facility location. Obviously, you can retrofit the MI variant.
Okay, go ahead.
So this just went through the sparse dense hypothesis, confirmed that semantic similarity are useful signals. And this alpha 0.7, so as Vishak asked how I came up with it, I constructed a tuning experiment. So I took over 2,000 examples and of the data set and optimized and found the accuracies over the graph cut MI only. Now the trend was like this. I observed that 0.7 was performing best. So Vishaka, this is how I found the 0.7 parameter,
So
sparse
what
dense
is this
parameter.
alpha is doing what? I'm just trying to recap. Alpha is
Yeah. This
Acha,
importance of
sparse and
sparse
dense.
dense.
Okay.
So 0.7 means sparse. The downstream data set has more utility for the this sparse signals, n-gram overlap signals.
So isn't it
Now,
counterintuitive that like 70% for the sparse retrieval than like more weightage to the sparse retrieval than the dense retrieval?
so that's data set dependent. That's a data set. I mean, the task is like that, I guess. And also, this is already 2,000 samples.
Okay.
So you have determined the alpha just using grid search, is it?
No. I think
No. I tried 0.1, 0.3, 0.5, 0.7, 0.9. I tried it manually.
And that's what. So that's the same as saying it's a grid search, na?
Oh, I'm sorry. Should I go ahead?
yeah, go ahead.
Okay, go ahead.
So the query relevance measure. So if there are improvements, not much, but there are improvements. So it models the cross document interaction as a multiplication rather than a difference logged at MI. Now the facility location MI completely ignores the query set and the input set interactions. So it's also benefiting. So which ignores it's benefiting. Now the best performing model here is BART large. I took the numbers from a paper called this is the paper's name. So I took the numbers from there. Now the actual best performing models are in the range of 72, 75, but they fine tune on a lot of tasks and these are large models. So this BART model is 5 times larger than my model. So I couldn't really experiment with that. My GPU was not, my GPU was running out of memory. But the point is that even the 5 times smaller model is competitive with this BART large.
For this training of BERT labs, where the ordering of the retrieved documents given and BERT labs
I'm
was
sorry,
tuned to the.
did not understand.
Yeah, so for the ranking part, this BERT labs was tuned with the ordering of the documents.
Ordering of the documents meaning?
So like this BERT labs, eventually they select a subset of the documents from the uh, retrieved
Normal retrieval.
documents.
Normal
Yeah.
retrieval, just like normal retrieval. They don't do submod anything, just normal retrieval. How did you do? Course, maximum inner product search over that, just the encodings. That's it.
Okay. And there is no re-ranking. That's what you said.
No. Just straight up select the 5, 10 documents, whatever. I had to do re-ranking because I want to do submod, and over the whole corpus it would be very expensive. Should I go ahead?
Yeah.
No re-ranking was performed.
Yeah. I mean, if you perform re-ranking, benefits will be there, as they usually are. Now, this is the end of my experiments, but I came across a very interesting formulation. So I don't have results for this, but I formulated a very interesting formulation. So observe that this is just a rough mathematical formulation of retrieval schedule drag. Just want to emphasize this is entirely new, at least in RAG literature. Now, if you observe
Sorry,
that,
can you present it again?
so retrieval scheduling in RAG, scheduling in RAG using submod optimization. This is a formulation. I don't provide results for it, but this is entirely new in the RAG literature using submod.
What is scheduling here mean?
I will tell you. So observe that the RAG problem poses no limitation when to retrieve and how to retrieve. So what usually people do is you have an LLM, you have a retriever, retrieve the documents and append as context. You have append context, you just do that. Now it's entirely possible what to do is you have a query, retrieve per token. You can do that even if that's dumb, but you can do that. Also, you may retrieve even amidst the forward pass of the transformer. Now, a realistic case is consider this query. What's the longest river of the 7th largest country in the world? Now, it's unlikely that an LLM will, from the initial retrieved set, will answer this query properly. The ideal way to solve this would be first retrieve the documents with respect to this part. Sorry, first retrieve the documents with respect to this part. What's the 7th largest country in the world? First do retrieve for this, then do retrieve for this with respect to the answer that you got from here. Now, if you were you to usually do it, what you would do is just take this query and just retrieval over the whole corpus, just take this embedding and find the retrieved documents. So you retrieve only once and for this entire query. The ideal way would be to retrieve multiple times depending on the query. So this is retrieval scheduling. Retrieval scheduling as in when to retrieve, what to retrieve, how to retrieve. Should I go ahead? Yes, sir.
So I didn't understand. What's the scheduling here? You start with
Schedule
7
as
largest country.
Schedule as in, so suppose you have a query, right? So normally what you do is you have a query, you encode it, and you take the MIPS top key retrieve documents with respect to the embedding of this query, right?
Yeah.
Now, what the ideal way to do is process the query and retrieve when it's actually required. So if you were to retrieve the documents for this entire query, it's unlikely that you would get the correct documents. But
Which
if you
query?
were to
Which query? Which one? 7th largest country in the world.
entire query, what's the longest river of the 7th largest country in the world? If you were to retrieve with respect to this entire query, it's unlikely that you would get the required documents which would answer this query. But if you were to if you were to first retrieve for this, the LLM decides that I would first retrieve for this query. I would answer this query. I would retrieve for this. Then when I get the answer, I will retrieve for this part of the query. It's dynamically saying that I will retrieve, when I will retrieve, how to retrieve. So this is the retrieval scheduling part. I'm sorry, my throat is a bit bad. So this is the dual formulation. As I so dual formulation as in that there's a very popular paper on limit former, which is which experiments with the dual variant, and I already mentioned that this is just my term. This is commonly called long context learning. Now, a brief primer of how a limit former works. So suppose this is the layers of the transformer, right? Now, what this paper does is retrieve for every head, or retrieve for every head of this transformer. Just retrieve it. For every head of the transformer, just retrieve the documents. Now it performs better than other methods, but the issue is you retrieve for every document, retrieve for every head. An obvious simplification would be don't retrieve for every head, just retrieve for some of the heads so that the performance increases or performance remains the same. So what they found is the top 4 or 5, I don't remember the exact number, but for the top 4 or 5 layers of Llama, they were getting the best performance. Now, no citation of the paper has considered retrieval scheduling as in selectively choosing which heads to enforce the retrieval upon. So currently it's retrieving per every head. What's ideal would be to, with respect to the query, it must be query dependent. So for example, for the earlier query, longest river wala query, just dynamically decide. So suppose I will retrieve for this, I will retrieve for this. Dynamically decide which heads should be active.
This is just a hypothetical layer. We are not implemented anything here, right?
No. This is just a formulation.
We have only 4 minutes left, so. Um,
Yeah, I will be able to.
So can you?
So
yeah, wind up.
So in an ideal world, what would we do is you have a query, you have a model J, and it will tell which heads to retrieve from. It will just tell. Now this is what we will try to achieve. So you have this model. Now you have training data set for this, which implies you have a query. You need the ideal heads. Now how will you get the ideal heads? So this is where submodularity kicks in. So anecdotally, there is some metric which has diminishing returns as the number of retrieval steps increases, and also an increasing number of retrievals can harm the metric, which implies the metric is non-monotone submodular. Side note: the log likelihood of LM possesses this anecdotally. It's observed.
What is LM?
Language model.
Okay.
Now the submodular formulation. So I will just go over this quickly. So I just said you need a training data set for this. For this query, what's the ideal subset of the heads? So very simple thing you do is formulate a similarity matrix as this. So for the ith layer, take the jth and kth head, and if they are active, what's the accuracy, and subtract it from this if there was no retrieval, as in no retrieval head was active. So this is the similarity scores between I and J. Now what you do is you compute the whole this similarity matrix, do some model optimization, and you have a subset of this subset of the heads in this layer, which will subset of the heads in this layer, which will which will optimize various objectives depending on the submodular function used. The point is it would be a subset of this. Now this is our training data set. Now what you next do is simply to train the J network, you minimize the cross entropy. So if these were the active heads, so you minimize the cross entropy over this. And we will have the J model. So now at inference, what will happen? You don't need to do some model optimization, just have the J network query and give the layer and the head index, pass it to this, and it will tell whether it's active or not. So I think I'm out of time, I guess.
Okay, so you have not trained this so far, right?
Yeah, so this work so these experiments took a lot of time. So these are a lot of experiments. So I just touched upon that.
What did you use in
retrieval-
MI? In MI again, can you remind me what was your formulation? Q. What was the query? Query was original query itself.
Hmm.
A was a set of documents. So you basically 50. So the final re-ranking via submod. In the final re-ranking via submod, what was the query?
Query was the original query.
Mhm.
Submod re-ranking is over the corpus.
Okay.
So
So
for a
Vishak,
query unit,
right. Okay. So, if you're interested in pursuing a paper around this, I think Vishak is quite relevant to what you have been doing, right? Can you talk to him separately?
yeah, sure,
Yeah.
sure.
So what is that no context, the first one?
No context as in query, you don't give any document to it.
Or just the query?
Yeah, yeah.
Okay. So why
So
didn't you not include top K here? Top K
Top K
documents or
meaning?
something? Like just taking the top K documents?
Or I mentioned that in re-ranking, I take the 5 documents.
okay, we'll have to end the call. So
Sorry.
Vishak will follow up. Vishak, please follow up with him. This
Yeah,
is
yeah,
very
sure, sure.
yeah. Okay, thanks.
Thanks, sir.
You move, Saral.
Yeah,
And
good
team. Yeah,
afternoon,
please
sir.
start this. You're presenting
Yeah,
now, right? 12:30?
yes, sir.
Yeah, please present immediately. We have to start on time. Go ahead.
Yes, sir, I've shared. Let me know when my screen is visible. So, is it visible now? My screen should be visible right now. Hello?
Yeah, it's visible.
Yeah, okay. So, our project, our seminar was learning to summarize from human feedback, and the project is on exploring summarization tasks through reinforcement learning, heuristic function settings. I mean, we have different environment settings, and we are seeing what kind of environment setting leads to what kind of summaries. So, environment settings and a few dataset formats will explained by Ayush, and then uh, PPO settings will be explained by Pranav, and then I'll conclude with DPO. Ayush, you can take up.
Okay, so good morning, sir. Good morning to all. And okay, so the environmental settings we are using here are first we will analyze the multiple settings with T5 based models. So, uh, like experiments using GPUs for fine tuning and optimizing via RLHF PPO, and alternatively via DPO also. So the T5 small model which consists of 70 million parameters that we are using at 2 seconds, 2 settings, and running it for 4 epochs and 25 epochs to analyze the efficiency. And this is like the vanilla approach for this. And these two model settings can be viewed as the supervised fine tuning model for summary generation. And also we are after that using T5 base model, which has 220 million parameters, and with multiple settings as a vanilla model trained for 4 epochs, and base model plus fine tuning plus PPO, and the base model with the PPO. And after that we analyze the results for these approaches and compare them and demonstrated it. And the uh, dataset used here is we utilize the human feedback summarization dataset provided by the OpenAI that consists of 110K instances of original text along with its chosen and rejected summaries as annotated by human evaluators. And for fine tuning and using RLHF on the model, we format the dataset as per the requirements of the available trainer for reward model, PPO, DPO and vanilla settings. So the steps we followed for the D5 model, vanilla models are: first we downloaded the RLHF dataset from the OpenAI dataset, that have the train and test dataset. After that, the database set was converted to data frames using Panda libraries and was cleaned and brought to desired structure. And for that, we removed the null values and duplicate values. And then the model and tokenizer downloaded from auto tokenizer and auto model for sequence to sequence LL library. So like these library consistently define small, so we use the auto model for sequence to sequence. After that, the data tokenized and training argument was defined, and the blocks for like, then we evaluated and then for evaluation and completed the method.
Your voice is not at all audible. Your voice is very feeble. Can we speak close?
I'll wait. I'll take up. So what we did was we have taken model and tokenizers from, like, usually the model settings is for auto model causal, but since we have a limited compute, so we have taken T5 small model, and libraries used what auto tokenizer and auto model for sequence to sequence LM. So, and route score matrix was used for evaluation. The code and the code base and the projects have the links are shared in the slides, in upcoming slides. And if needed, we can go to the code base and we can verify like all these things. So these are the train and eval loss graphs for sample size of around 30,000 and 4 epochs we have run. So what we have observed was, for initially, let's say for 4 epochs, the model summaries were kind of okay, but but when we increased the epochs to 25, the summary started to become very compact. We'll see the examples of what I mean by compact. For now, I'm leaving it at that compact word. And then we also used the stemmer. Stemmer was to, like, for say example, there is a word running, so we brought it to the base form, say run, so that when a, a text is getting summarized, so the road score should not get affected by, let's say, for running, there are different words, run, walk, or road score won't get affected using the stemmer. And since we have used OpenAI database, so not much of a cleaning was needed, but just for verification of if there are not null values or duplicate values, which was already mentioned in the previous slide. And yeah, database that we have taken played a very important role in getting good summaries. So the summaries generated example can be found in the link below. Yeah, this is what I was talking about, the epoch 25. Though there was a decrease in loss for training and validation loss, and the row scores were good, but we were getting very compact summaries, and those examples are given in the link, also given in the link below. So now coming to the T5 base model, earlier we were discussing about T5 small model. So T5 base has significantly more parameters. So we also use the T5 base model to check how good our summaries, how good this model will work for a given data set. So I mean, while training our model, after 1 epoch, there we were seeing like the training was certainly going to zero, validation was not a number, and therefore the road scores were not valid. So we had to reduce. So we basically increased our data set, and we modified our T5 base. And on the right hand side, the training loss for modified T5 base output. This is the output that we got for epoch. We ran for only 2 epochs because I mean it took a lot of compute time for further epochs. So we stopped the model at 2 epochs, and the training loss and I mean training samples per second and steps per second, train steps per second data has been
So
given here.
I'm still wondering what you have done so far is you just have taken the T5 small 70 million parameter model with 2 settings, 4 epochs
Yeah.
and 25 epochs, And they basically the two model settings you have viewed them as supervised fine tuning model for summary generation. And
Yes,
then
sir.
you took a
Total.
T5 base model, 220
Yes, sir.
million parameters with multiple settings, 4 epochs, training base model plus fine
For
tuning.
many with PPO, and then last is for with DPO, direct preference optimization.
So, so basically, but so far you have looked at all of this through the lens of training and validation loss. Now, when you say loss for summarization, what does that mean? Root score, I understand. The loss is basically cross entropy at a token level.
Yes, yes, sir.
And then root scores, so you're saying your observations are that basically Rouge 1, actually, which, so the sample size 180K epoch, you're not able to compare across sample sizes and epochs. So for each sample size epoch, you just said, okay, training validation loss are decreasing, root score,
The
and your
the
general
comparison,
observation.
sir, the comparison is at the last slide.
Which
For
slide?
in the last, I mean, I'll have to jump to it. Yeah, this one.
Okay, you have
So
not shown this
T,
so far.
yeah,
You're
not shown
just,
for so.
so far you just individually done some sanity checks.
Yeah, we are also the code base. I mean, we have not just this is not Git repo cloned and implemented. The T5 model, whatever code that I have written, like it's own data, own code base, not just Git copy and implemented.
So can you repeat again?
The code base that we have used for our different environment settings check our own code base, except for
Mhm.
like importing T5. I mean, that is pre-trained model importing and road score library and LoRa configuration. I mean, Hugging Face library for LoRa and PEFT. Those things are imported. Rest of the things like for T5 small models and base model, whatever that we have done is like it's our own.
Okay, continue.
Yeah, okay. Yeah, so this was done. Yeah, PPO will be explained by Pranav.
Okay.
Yes, sir. So as we've seen till now, the approaches have been based on the vanilla experiments that we conducted via D5 small, and we also used D5 base, which was
But oh,
developed
the comparison you're presenting at the end, is it? There's no
yeah,
comparison.
yes.
You said there's a slide you have comparison.
We'll be showing the comparative results and the plots of PPO and DPO as well to show how their efficiency increases. So when I worked on PPO on D5 base, which is the 220 million version, and I've just described in brief here what PPO does, and this is some information that I found online because I've not gone to PPO earlier, but I'll just explain
Just a
how
sec.
its optimization step works. So proximal policy optimization is based on a key new topic that they introduced in the paper, which is called proximity. Proximity constraint helps in keeping it's sort of like a clipping parameter which ensures that the updates of each iteration are not too far from the previous policies. And this clipping is aimed at extending the updates to avoid sort of abrupt changes also. And some of the advantages that it brings by using this constraint is that
Where is
it
clipping?
is
Sorry, I didn't understand. Where is clipping here?
clipping happens in terms of to
But
reduce
where?
the
Which? Where? I'm not understanding. In this slide, there's no mention of clipping.
no, that I'm just explaining from what I understood from the paper. I did not add it here. This slide is just a brief description of PPO which I found from medium.com. So clipping, I'll just okay, I cannot visually explain clipping here, but clipping is sort of where proximity is used to
Sorry, your
confine
slot is 12:30, is it? Your slot is 12:30, is it?
yeah, yes, sir.
Okay, and I think Spandan, you're at 1 now.
Sir,
Spa-
we were told to be at 12:30.
No, Vishal, tell who's the when now? Because I think Saral, you please continue because we are just following the calendar. So Vishak, 12:30 is this team, and then 1 o'clock is Spandan, right?
Yeah,
Vishak,
like
Vishak.
we will have to move one slot. Like there is also one other team at 1 minute.
Yeah, then move. Yeah, then they can come at 1:30, no? Is there a team
Yeah.
at 1:30? Or at 1:30 also there's a team? Okay, go ahead, Saral. Vishak, you just adjust in the meantime, yeah.
Yeah, sure.
Yeah. So again, as it's described also sort of in an abstract fashion about clipping, that is just done to help the iterative approach where there are not so many abrupt changes, or the policy doesn't move too far. The updated rewards or penalties do not move too far from each iteration to keep it close to each other within the proximity parameter. So that is because they state that it is helpful for giving stability, and that is crucial for RL scenarios. We do not need the reward to be updated in sort of a manner where the changes are abrupt and say for a particular reward the penalty goes haywire, and it's sort of deviating from what the range of reward should be. So to clip that and limit the range, they are using a particular proximity parameter. And this talk about how it helps in scalability and efficiency. So again, I also implemented PPO through Hugging Face also only, but it was based on T5 base model, and we were able to obtain these results for training for 4 epochs. It took some time for 4 epochs, that's why it's only for 4 epochs. And you can see that the losses when we are applying PPO to this model are coming close to 1/4. For the T5 small graphs that were presented, the range was around 2.5 to 2.8, the training and validation loss. But here it's coming within 0.7. So, and we've just given some sample results also to describe how PPO and later on DPO, which Saral will explain, how these are providing better summaries along with the loss and root scores in a tabulated manner.
So far you're saying PPO gives BPO and maybe as you also present DPO have lower losses and better quality summaries.
Yeah.
Yes, sir. And also, one more thing is that the seminar paper that we went through, the OpenAI had presented PPO and how they were implementing it. But for that, they also had to train the reward model, and computation costs go in that as well. We also found that during the training of the reward model first and then PPO. That is where again DPO, which Saral will explain, it gives better results, and it is a direct one-step stage where we take the preference data and use DPO on the base model.
Okay,
Yeah, please go ahead.
so DPO is direct preference optimization, and I will not dwell into too much because we don't have much time. So I'll keep it brief. DPO is from the image we can see that instead of a reward model, I mean we are directly giving the preference data. So why not use those preference data directly, and then we get our final LM model. So the cross entropy loss is in the right hand side of image, and they are labeled like we are using logistic loss instead of using KL divergence with the reward. We are directly implementing difference between the KL divergence. The shift between the preferred completion, that means the preference summaries, and shift in the dispreferred completion, that is how much summary has been drifted towards a rejected summary. This is small, just the gist of it. Okay, so I'll move on. Yeah, so we have used DPO along with T5. The motive behind using the DPO is to avoid too much of a GPU compute time, because the file size increases, so we need more GPU time and GPU computing power. So, like for example, initially we started with Mistral model, but Mistral model around approximately needs 40 GBs of whole after computing your model weights, your Adam optimizer, and all those things will approximately cost you 40 GBs of compute space. So we do not have that kind of compute power. So we switch back to T5 base, and thus.
Sorry, I lost you. I lost you for the last 2 minutes. Can you just repeat what you
Yes.
don't have?
Yeah, so we initially thought of starting with the Mistral, but Mistral will take around 40, final model will take around 40 GBs of compute, I mean 40 GBs of space. That will include all the weights, all the parameter, all the atom parameters. I mean the hyperparameter training, all the gradients, all these things will approximately take 40 GBs. That is why we switched back to T5 base model. And because we switched back to T5 base model, I mean, DPO can be classified into two parts. First is reducing the precision from LoRa and PEFT, and the second is quantization. That means we are moving the precision of 32-bit or 16 bits to less precision. Let's say float 16 has been moved to integer 18. Sorry, integer 8. So that is what quantization means. But since we are already using T5 base and we don't have too much of a storage, so we have skipped that quantization part. So we brought the data set used here are different from the data set used in the previous models. So the data set, the Hugging Face data set link has been mentioned here, and then the data set has brought into this format that is in the figure in the image above. So the next step is data collection and optimization of maximum. Optimization is basically maximizing the likelihood. So this optimization happens internally when we pass the PEFT configuration, and when we train our DPO. I mean, when we mention in the image, we can see like when we define our DPO trainer, we can send tokenizers, and I mean we have sent data set, raw data set to train. We have sent evaluation data set as well. So these are the configuration settings on which we have to used DPO trainer. And the model and reference model here means the model in which we will be the model that we will be fine tuning, and the reference model is which is referred to make sure that the model which gets fine tuned does not deviate too much from the required summary. So also we have used float 16 for both of the model summaries instead of brain float or F32 to keep our precision bits small, and thus memory requirement small.
Then why are you saying
So
quantization? Can you go back to the previous slide?
yeah, so
But
quantization I mentioned just because, I mean there is a concept of quantization in DPO, but we are not using it. Just to make I mean to clarify that what quantization is, I mentioned it. I mean there is a I mean when looking DPO in Hugging Face library, we can see there is a part of quantization in which it says the model has to model is going through quantization part, which basically is to reduce the precision bit. But we didn't take that because we already have small model and not much large of a data set we are using. So that is why I mentioned quantization. So yeah, PEFT is parameter efficient fine tuning, and PEFT has many optimization techniques, LoRa, LoHa, and adapter fine tuning. But what we will be concerning with ourselves with the LoRa. That means LoRa adaptation. And the configuration settings we have used are sequence to sequence LM. That can, I mean, there are I think 3 to 4 types, task types, such as question answering, text generation, sequence to sequence, and causal. I think these are the 4 ones that I saw. We have used a task type sequence to sequence LM because our model was the model's task is to summarize basically. So R here means the attention head. LoRa, I mean, we can see LoRa as a matrix decomposition. I mean, it decomposes the large matrices to smaller matrices. So let's say if we have a large matrix of D cross K, so it will reduce that matrix into D cross R and R cross K. R being the attention heads. I mean, we can see as attention heads. And target modules are QV. That means query and values. Since we will be giving a textual format, and what we'll be receiving is the final summary. Okay, so these are the results. I mean,
sorry, can you go back? Can you go back to the previous slide?
Yes, sir.
I see. This is on top of. This is not on.
This is on top of T5 base. I mean, T5 base, instead of going through RM and PPO, we are going through DPO.
This is through DPO.
Yes, sir.
Okay.
I mean, I can go to the initial slide. I mean,
Go
when
ahead, go
I
ahead, go ahead. No, no, go ahead,
yeah,
go
okay.
ahead. We won't have time.
Okay, okay. So these are few results. I mean, rewards chosen, rewards rejected. What are the rewards that are given to the chosen ones? What are the rewards that are given to the rejected ones? I mean, these are the like brief summarization. Uh, and analysis I've posted on weight and biases link. So wait, I can go to the link and maybe for yeah, okay. So as we can see for train rewards that got rejected, we have this graph. It usually should like it should go to negative weights. Negative values. Sorry, that your reject the rewards that if our model took the rejected one or the rejected summary is similar to what our generated summary is, the reward value should go to negative. And accuracies, as you can see, for we have taken only 200 epochs. Usually this runs for 100,000 epochs, but we have only taken it for 200 epochs. And we can see, for even for 200 epochs, we are having slight increase in reward accuracies.
200 epochs for DPU.
Sorry.
200 epochs for DPU.
Yes. Yeah.
Okay.
Yeah, you might think that it will take a lot of time, but we have reduced. We have not taken that. Gradient accumulation and precision format changing. So that it reduced our training time to a lot, like in lot of factors. So for we can see a gradual decrease in training loss as well. Okay. So yeah, so this is the final slide.
Go back to the weights and biases page.
Yeah, okay.
Okay, fine.
Yeah, so there is one more graph. We have used cosine training rate for first 100 steps. I said we have set it to like linear and then cosine degradation. Okay, so coming back, yeah, so this was our result. This is the final model comparison. So these are for these settings. T5 small we ran for epoch 4, T5 small for epoch 25, base for epoch 2, because for uh, for more epochs it was giving 0 directly. For PPO and for DPO, similarly for 4 epochs. Yeah, so before conclusion, I would like to share one comparison summary. So this is the this is the text that we have taken, and these are the generated summaries for each of the models. If you have like for a T5 small vanilla epoch, it generates some summary for as I mentioned earlier, for vanilla epoch 25. It started it started giving very compact summary. Met a girl, broke up, met up, didn't sleep. It's very compact summary. But when we you switched our model to T5 base epoch 2, we had these are the summaries for different model settings for a particular textual data. So this is also mentioned in the this text is also in the drive, and all our code bases are also mentioned in the drive. With the with the outputs stored for all the settings that I have already mentioned. Finally, we would like to conclude that T5 base model outperformed the T5 small model in generating summaries. It was already it was expected because T5 base has a larger model, and when training on a larger sample size, T5 base has to outperform T5 small model, and that is what we observed. Training challenges were basically, the GPU compute and precision changing format. Once we had a issue with the precision format. Initially, I trained it on the model, and reference model that I gave was float 16, but the model that was saving and loading was, it was returning the values in brain float point. So these few minor training challenges we had. And the data quality obviously played a huge role, because when we changed our data to data for our DPO, we saw a spike in generating summaries. So ML model when aligned with DPO gave better summaries, even though the training loss is as high as 0.59. So yeah, okay. So I mean these points I've already mentioned. So increasing the rank variable. One more settings that I've changed was rank variable. I mean initially we have taken rank variable as 2 or some 8, but when I increased the rank variable to too much, summaries did not improve. I mean they were more or less the same, or it might have degraded. So these are the references where we have referred. I mean DPO paper has been
Can you go
mentioned,
to
and
the
all.
43rd slide? You can skip the reference. Can you go to the 43rd
Yeah.
slide? Yeah. Yeah, where is the validation loss for T5 base?
Yeah, actually, validation loss. We had a validation loss, but I mean, the GPU. Sorry, not the GPU, but Collab got disconnected. So I mean, we lost that the whole the training loss. I remembered because I saw the training loss, but validation loss I was not able to recall what validation loss was. That is why I mentioned blank over there.
Yeah, because like you have performed PPO and DPO over T5 base. So we need to compare with the T5 base validation loss, right?
Yes, correct. So I mean, if we had to, it would have taken around 5 to 6 hours just to run 2 epochs to get a validation loss. So I mean, we moved to like to PPO and DPO.
Okay, thanks. So I think I got your conclusions. Um, you, I think all the learnings will be helpful for you in the future. That's pretty
Yes, sir.
comprehensive. And what do you mean LMM model when aligned with DPO? You mean
Yeah,
when you use DPO?
yes, correct. I mean, in this RLHF now,
Got it.
we train our model on reward model and then PPO. Instead of going through reward and PPO, we aligned it with DPO. By alignment, I mean by reducing the precision bits, by setting configuration to LoRa and PFT. What that further means is it is a concept where we freeze the model weights, like the initial model weights are freezed, and few layers are inserted in between, and only those layers are fine tuned. That is what it means. Basically, it means by aligning the DPO. I mean, aligning your model with the DPO. And
Got
these
it.
are, I mean, there are various, I mean, you can say optimization techniques. I mean, either you can fine tune your last layer, or you can insert new layers in between your present layers and then fine tune it, or you can use LoRa, that is low rank adaptation. And I mean, there are various optimization techniques such as as such.
Okay.
So yeah, so I think we have completed within 30 minutes. If you have any questions, you can, or I can, and the code bases are also, okay, this
Okay.
got if
But I
I
think it's
mean,
okay. We'll move to the next presentation. No time. Okay, who's next?
okay,
Vishak, thanks.
thank you,
Yeah,
sir.
Spandan is next.
Thank you.
Spandan group.
So okay, so we don't have any other presentation, right? Go ahead.
So we don't have. So I have shifted one presentation to 6:30. That's so fine.
No, 6:30 is not possible. 6 o'clock is possible.
So 6 o'clock already one presentation is there.
Okay, fine then 6:30. Go ahead. Spandan, you can go ahead.
Sure, sir. I will just share my screen. And is it visible?
Yeah.
Yeah, I suppose.
You don't have slides. You don't have slides, is it?
No, sir. We thought that there won't be actually a presentation, and we thought that just the report would be.
No, I've been saying presentations and slots were announced today.
Yes, sir. We had a misunderstood that.
No, everyone else has been presenting. You saw. Okay. Okay, go ahead.
Uh,
Your two of yours.
Yeah, I'll start the experiment. So can you go to the paper?
Right.
Right. So our work is based on our seminar paper which we performed, which is basically explicit regularization using noise injection. So basically, we were injecting Gaussian noise into gradient descent, and we observed first conclusion that we observed was that we are getting an explicit regularization. And the second major conclusion was in terms when the models were over parameterized, then when we added noise to all the layers simultaneously, then like the loss function was exploding. Like we had variance explosion problem. So they employed a layer-wise independent layer-wise perturbation, where only one layer is perturbed at each gradient step, and using that, then even in over-parameterized models, this gradient noise injection in gradient will work. So in
Sorry, can you repeat once more?
right,
Just
so
start from beginning.
yeah, so this is in this paper. This is basically noise injection in gradient descent. So basically, there are two key observations in this paper. First one is noise injection in gradient descent, which is a Gaussian noise, gives explicit regularization in finite dimensional models. So that is the first one where they actually show mathematically how it is explicitly regularizing in terms of loss function. And the second one is that uh, I'm not pleased, right? Yeah, okay. The second one is that in case of over parameterized models, there is a problem called variance explosion. So in that to solve that variance explosion problem, we perturb the layers independently, layer wise, not all the layers at once. We add the Gaussian noise to some particular layer, and that solves the problem of variance explosion. And using this method, like they have tried on or they've tried until like basic models, finite dimensional model, and on neural networks, and one layer and two layer neural networks, and also on very wide neural networks, so that we check that variance explosion is happening or not. And they have confirmed in the result that this is performing better than without adding noise. So one thing which they did not
No,
perform
so they are saying that without adding noise, there is variance when there is Gaussian noise injection in more parameterized model. There
yeah,
is variance.
in wide networks, in over parameterized model, if we add all the Gaussian noise at once, then there is variance explosion. But if we use independent layer-wise noise addition, then we solve that problem and we get our explicit regularization, and it
We
performs
use
better than
independent layer wise.
layer-wise injection of noise. Like our neural network is there, so we only put noise on one of the layers instead of all the layers at once.
Mm-hmm.
And that
In
layer
one,
is randomly selected.
yeah, during different epochs.
If we use independent layer-wise injection of noise, then what happens?
Then the problem of variance explosion is not there. The variance explosion, basically the loss function explodes if as our hidden layers width increases to infinity. So
I see. So that is their proposal. That is their
yeah, that is
contribution.
it. Correct. And they have tested this on normal neural networks, and additionally also they have also tested on CNN, which is on MNIST data. For that, they don't haven't provided mathematical formulation, but they have provided on this data. So one thing which they did not perform was the gradient descent after injecting noise after the gradient descent. So what they did was they injected noise before performing the gradient descent. Like the noise was only added to the gradient calculation, but the step was taken on the before on the previous parameters only. So they have not checked if we add the noise after the gradient descent, then how does it perform. So our first proposal, like we try to improve upon, is adding this after gradient and checking whether how it is performing compared to that. And we also extend upon this to extend this to more complex models, which are recurrent neural networks and LSTMs, like transformers. So yeah, you can move to the report, our report. One.
Okay, so that entire finding has been gradient injection before gradient descent. Gaussian noise.
Yeah, only before gradient descent. That was one of the drawbacks that we mentioned.
Hmm.
So can you move below? So this is the previous work that we have. Yeah, so now we try to introduce inject noise on both before gradient and after gradient and compare them simultaneously. And we perform so go one step below. Yeah, we perform experiments on more complex models as well. So firstly, I'll explain the main algorithm how we perform before gradient descent and after gradient descent. So here you see that during training, if my noise is not no, that means I am adding noise for each epoch. I am firstly copying my parameters into another variable. So all of my model parameters are copied. Then I add noise to our original parameters. If all layers setting is there, that means I'm adding to all layers. Then I'm adding that to all layers. But if it is layer wise approximation, then to that particular layer I'm adding noise. But that noise is added to the original parameters, and our copied parameters are saved somewhere else. Then what we do is we perform a gradient descent. Scroll down. Yeah, we perform back propagation and gradient descent, and after that, our if we want before gradient, then this if function will work, and the following code will execute, where what we do is we perform step on the copied parameters. So we have saved our previous parameters and we update them with noise injected gradient. So that is basically before gradient descent. And if we have after gradient descent, then we do nothing. Then it's just the original, because we added gradient and we performed gradient descent on that injected noise only. So in that way, this code covers both after gradient descent and after noise and before noise. Also, like both are two categories: all the layers and independent layers.
Okay, so you have provision for both before and after.
Yeah.
Right, and you're going to compare the effect.
Right.
Okay.
Yeah. So Spandan, can you? Yeah.
Sure. So what we first started with was that we tried to check the baselines which they have actually implemented in the paper. So the first one of them was the F-MNIST data, which is the fashion MNIST, and in which they again have grayscale images, and we want to perform a classification task on them. So for this, we have utilized three different models. So the first model is three layers of 500 neurons. The second model is 3 layers of 5,000 neurons, and the third model is 5 layers of 1,000 neurons. So using this, we compare with the results with what they have gotten. Another point is that because they had a lot of resources, the number of iterations they have trained for is very much high, and we could not train it for that many epochs. So we increase the learning rate a bit and decrease the number of epochs, so that we could also get some results in the finite time. So so this is the comparison between their results and our results. So here, as you can see, we have 5 different components, no noise added, layer-wise noise, and noise all, which refers to the before noise, as they have shown in the paper. And another extra component is noise, adding noise after gradient descent for all layers, and adding noise after gradient descent for only a randomly selected layer. So we just compare these for all three of them, and we found out that for the small layers, uh, as you can see, only the second layer is quite huge with 5,000 neurons in each layer. So it is quite a wide layer. And for that, we find out that the noise adding noise before gradient descent at all the layers, it actually gives us much lower results. As you can see here, the the accuracy values is much lower here. And for the remaining part, these almost give us the same results, but without adding any noise and adding noise, layer-wise noise, after gradient after descent actually gives us some slightly better results. So this is something different. I mean, add something to add upon than the paper, because in the paper they have not performed the after noise part, and here as we can see the after layer wise noise actually gives us better results than without adding noise. So this is the result for the F-minus part. And second, we move on to the CFAR10 dataset which they have used. So the CFAR10 model is again much more bigger and is much more complicated compared to the earlier one. So here we obtain the following results. So in the paper, as you can see, the just the simple SGD gives performs not very well, but adding layer-wise noise before gradient descent actually gives us better results. So we tried doing that, and we found out that uh, this actually was only true in case of layers where the model size was quite large. So if I mean, by the model size, I mean to the depth of the neural network as well as the width.
So
So
you're
if
saying before is you're saying before is better than after
yes,
everywhere.
here as you can nearly everywhere. So here in the earlier case, the before part was actually performing worst because the blue and the purple line, they refer to no noise and noise after layer. So this part was a bit different, but in
The earlier means on fashion amnest and on fashion amnest and
on
earlier was doing worse than later, right?
yes, for the fashion MNIST, the layer wise after noise was performing better. So this was something to add upon that they did not do in the paper. And in the second part, as we can see in the first two CNN, which are quite
When you
small.
say second part, you mean CFAR?
Sorry, CFAR. In the CFAR data set, in the first two models, which are actually not that big CNN models, we
Noise
found out
before
that
GD was better.
noise, no noise was actually better. So without adding noise, we converge faster compared to adding noise. But when we increase the size of the
Wait. CFAR 10 noise before GD was better, no?
Noise before in their paper.
Whatever you're reporting.
No, in our reporting, we found out that for it was only better in case when the model is of a large size. So if we have multiple hidden nodes and layers, then this holds true. As they have mentioned here, that for a deeper and wider CNN, they got these results. And for the CNN3, which is actually deeper and wider, we get the same results. And we have also run it for the shallower CNNs.
Achha, let me just summarize. So you're saying both fashion amnest and smaller models, we have obtained that noise before GD is worse, or noise after GD is better, right? Whereas when model is large enough, then noise before GD is better than noise after GD, right?
In the first case for the F-minus part, we found out that the noise before is a little bit better. But in the CFAR data set,
no, fashion amnest, you said noise after GD was better. I'm very confused now.
No, wait.
You're
No, in F-minus, fashion MNIST, yes, the noise after gradient descent is a bit better.
Yeah, that's what I'm saying, but you contradicted again. Okay. But in CFAR 10, noise before GD was better than noise after GD when model is large enough.
Yes.
And that's just like them. But you're saying when, but on CFAR 10, when model is small, then noise before GD is worse.
Worse than adding no noise using vanilla gradient descent.
Oh, and how about noise after GD?
No, noise after GD performed very much more worse. The red curve and the purple curve here say tell us about the after GD, and the accuracy increased and then it dropped.
Okay, noise after GD always perform worse for CFAR10, right?
Yes. Yes.
Irrespective of model size.
Yes.
Yeah.
Okay.
So again, this tells us that as shown in the paper for deeper and wider CNN, adding before noise gradient descent performs much more better. Then we move on to MNIST dataset, which they hadn't tried upon, but it is again simpler. And here we again find out that this gives us similar results. So in this diagram, the middle model MLP2 is actually both wider and deeper. So for this model, we find out that the noise layer, the before gradient descent noise gives us better results compared to adding no noise, and adding after noise gives us the worst results.
So adding after noise always gives worse result on CFAR10, but the model is larger, then noise before GD is better than noise.
Yes.
Then no noise, right? Then no noise, and also noise.
Then no noise. Yes.
Okay.
So similarly, we tried to find out the Hessian as they had also just take a look at how it seems. But the Hessian was giving very much random. The values were changing very randomly. Only in the case of the second model, we found out that there is a definite increase in the Hessian when after noise, in the case of after noise. So the Hessian is basically the Hessian trace of the gradient matrix. So when we calculate all the gradients, then we found out what's the trace of the Hessian we get, and which tells us what's the size of the actual gradients, which was found to be exploding in the case of after noise. So this is for the minutes, and then we actually started for some to use the same technique for some different tasks. For example, we use sequential tasks such as text classification, where we have to tell the sentiment present in a given text. For this, we use the famous transformer type of structure, and we used it to classify the IMDb movie reviews. So these are just the key features of the transformer, and which I will just skip right now. And yeah, so these are the hyperparameters which we use for our for the different versions of the transformer. So in the important point is that in the first model the hidden size was 64 and we had 3 transformer layers. In the second one again we had a 64 size and we had just a single transformer layer. And in the third one we had 128 hidden dimension and 6 transformer layers. So now when we take a look at the transformer, we found out that uh, for the first type of transformer, which is of medium size with respect to both the hidden dimension and the number of transformer layers. In this case, the layer-wise noise gives us the best results, and the noise after gradient descent gives just slightly worse results than that. So here both of the noise, the layer-wise noise, both the before and the after gives us the highest results. And similarly, when we just increase the size, we for when we make the number of layers in the hidden in the transformer architecture very large, we find a surprising result that noise all gives us the best results. So as to say, adding noise on the entire model itself at the same time actually outperforms all other available methods.
Okay.
So this was regarding the transformers. Then we moved on. We tried using another famous sequential architecture, which is the LSTM model, and I used the bi-LSTM model to perform named entity recognition, which is a technique, which is a task in NLP where we say that for a given sentence, which of them are proper noun and what kind of proper noun are them, like a name, place, etc. It's again a classification problem, and this is the model which we use, which is an LSTM in bidirectional LSTM, so that we can take the input from both the forward direction and the backward direction at the same time. So the results for this were that all of the models, all of the techniques perform nearly best. So here the accuracy is in 0.1 and so on. So nearly all of them perform best, but it is seen that as we increase the number of epochs, the after noise part actually continues to decrease. So this is one of the issues which we have continuously found in the after noise, that sometimes when we run a lot of, when we keep on running the same epoch, a lot of iterations, instead of overfitting, the after noise actually tends to decrease the results. As this is not only for the test accuracy, but even the training accuracy also decreased. So this is one point, but overall the results which we achieved using this were the same. And afterwards comes the time series prediction, and in which we obtain really surprising results. So for here we use a simple LSTM model and just a single layer, which is this is the structure of the LSTM. And we again, for this model, we tried with different values of noise.
I'll
And
take.
okay.
So it's like we have changed the variance or the uh, sigma values, and we found that for lower sigma values, which is more noise, which is decent enough noise, 0.03, we find that the after gradient is performing faster. So in this LSTM model, can you go a bit down? So in this, on the graph. Yeah. So in this LSTM model, we found that over a large number of epochs, they all converge to the same loss value. But what happens is LSTM after noise is performing faster. So it's going to global minimum faster than the other layers in both train and test loss. So this is when sigma is 0.003, where after noise is actually performing better, and no noise is performing the worst, where rest is somewhere in between. And also after noise is on all the layers and not independent. So that is also surprising that it is performing faster. But it's not like that accuracy is changing. Accuracy is almost same, but it's matter of faster.
Okay, so
But
that's the surprising part. It is converging, converging faster, but overall it's the same.
yeah, but like this is after noise is performing better, so that was surprising. Like before,
Performing better is converging faster, no? But
sorry,
performance is eventually the, but
performance is correct.
eventual performance is the same.
Yeah. So if we even decrease the noise, can you go below? If we decrease the noise, actually the noise injected are performing worse. Like the no noise is almost performing the best, and the rest are almost the same. And they are and the LSM with before gradient with all the noises, some exception, it's performing slower. So if we decrease the noise or less, it's looking like a problem. Like it needs some noise. But also,
Decrease the noise both before and after.
yeah, both before and after are performing a little worse than like worse means slower than or no noise. It's almost same, but just one is the green one, which is the
Okay, fine. We need to conclude in 2 minutes. Yeah.
yeah, it's almost. And the last one is obviously if we decrease the noise too much, all of them are performing same. So that is there. Yes, one can conclude.
Okay, so for the conclusion, we found out that for different data sets. These techniques give us, I mean, we have actually tried to compare with the paper, and we see that a lot of the results match compared with the paper. So for the F-minutes data set, for the F-minutes data set, we found out that how the results are nearly the, I mean, the results are quite comparable, but the before adding noise gives us slightly better results. And in the CFAR, we found out that when the model size actually increases to a large extent, performing before noise or gradient descent actually gives us much more better results. And this is an important point because in a lot of the current architecture present, as we increase, the model size keeps on increasing. And in such cases, we can attempt to see if that this actually works. So quickly summarizing, so these are the results which we have gotten. And we have also implemented it for the sequential task, and we see that adding noise, adding a gradient before gradient descent noise also gives us slightly better results, improves the results in case of sequential transform. So this is done. So do you have any questions?
No, I don't have. I think we can. So there seems like this is some delta thing. I don't know whether we can get a paper out of this, Vishak. I don't know, but yeah. Do you think you will be able to work on a paper? We can stop screen sharing. The next team can start.
Okay, sure.
But do you think you guys are doing your MTech?
No, sir. We are currently in third year BTech of original physics, and I mean we can. We can try to see if we can try to get.
Next team can start screen sharing. Next team can please start screen sharing. Yeah. Yeah. So I think as they bring it up, I will get back to you. And if you also can get back to one of us or TAs, we think there is some interesting publishable material that comes out of this.
Sure,
right?
sir.
You need more work. You need significant more work.
Yes, sir, of course. Thank you, sir, and really sorry for what happened in the morning.
No problem. Thank you.
Thank you, sir.
Can you please start? We don't have time.
Yes,
we are sticking very much on to time.
Sir, I think it's not able to share. Just a second.
No, everyone, Azim is able to.
So 1 second.
Everyone has been able to. I don't need to do anything.
Is it sharing?
Yeah, we can see.
Hello.
Yeah, you can start.
Yeah, so basically in this project, what we did is we performed unsupervised object classification on fast RCNN. So basically we tried using cage and joint learning to do this. So we use the Spear library for this. So the basic motivation for this was there is scarcity of label data, so we should be able to get good accuracies with unlabeled data as well. So to try this out, we are performing this experiment and introducing this concept of using cage on CNN networks. So what we do is basically we have 4 base models which are basically your labeling functions, and we perform this on 20 classes. So we have 20 classes for object detection, and the 4 models which we use are ResNet 18, VGG 16, Inception, and ResNext. So our using our labeling functions, we use both.
Which are the four? ResNet 18, ResNext, VGG 16,
and Inception. Inception V2. Yeah.
What?
So basically,
Okay. Yeah. Go ahead.
yeah. So basically, firstly, we train all of these 4 models on the for our 20 classes. So it's just by changing the last layer. And now using Cage, we apply the labeling function. We use the models in the labeling functions. So like as the labeling functions, there are 2 types: discrete and continuous. So I would like Jay would continue from here about the labeling functions.
Next page, please.
So also I'll talk about the contributions once again. So what we do is we use Cage to build the labeling functions, as said, incorporating all of the 4 CNN models, and then finally we perform joint learning on the fast RCNN model by the parameterized labeling, the graphical model which we get from the Cage. So we perform joint learning on fast RCNN, and our aim is to prove that the training using the unlabeled data has a superior performance from the baseline fast RCNN. So yeah, ahead with Jay.
So actually, so mainly we focus on the unsupervised learning using the Cage method. So it's just we want to use that unsupervised or unlabeled data, unlabeled data for our training fast RCNN. So for that, firstly that we introduced the Cage model. That's we use the paper that published by. And so let's say X denote the sample input instances and Y is our label space. So we want to map with the Y with our inputs. But we have available alerts, so that can assign the particular label to that particular instance candidate. So particularly lambda j has a kj associated with it. Kj is basically that's a class. So that if that's a is that if it's a discrete labeling function, then it would be a discrete label called
Yeah,
tau.
your voice is very You're explaining Cage. Your voice is very muddled. I can't hear properly at all.
Hello. Am I audible? Hello.
Yeah.
So that for that discrete labeling function, so we have a discrete label called particular tau ij. So it will be triggered when that particular class triggered when particular class. For instance, that would be class associated with that particular image or kind of things there. So for that labeling function that we are using the prediction from the model that we had previously, that it should be ResNet or ResNext, or it would be VG16 or can be anything. So we will assign in we assign in prediction to that particular class, particular image set, using labeling. And the continuous scorer will be assigned the continuous score to that particular image. That might be the probability of that particular class or kind of thing. So, what means here that we mainly takes the from that Cage paper that is available on that online available that we use that paper. So this is a training objective that you mentioned mainly that's really using some potential function of the parameter theta and pi. That basically weights the prediction of the particular labeling function of kind of thing, theta and pi.
So, and for joint learning, that for we have that we can have the labeling or unlabeled labeled data or unlabeled data, and we might use them for training the both with cage model, that would be a graphical model, and the feature model, that would be a fast RCN, to train both of them together. So, and for that
So
we are
also to add on, like just to give a view of the labeling function, we have mentioned it in the appendix. So this is the example of the labeling function which we used. So basically, the probability we pass the model and the class through the model through the quarks, and with this we find the last probability of the prediction using softmax for both continuous and discrete label functions. So like these are the labeling functions which we use for all of the classes and all of the models. Now continuing to the methodology. So our methodology, it firstly begins with designing of the labeling functions. So what we do is we build 168 labeling functions, as we have 21 classes, and
so what are these labeling functions? I'm just looking at your labeling function. If LF1C0 image, if prob name. So what is it doing basically? Class of aeroplane. What is it doing?
So actually there are 20 classes in that MS Coco dataset. And so MS Coco dataset is basically for the object detection. So for that, we cropped images according to the given coordinates in that MS Coco dataset, and we are using those cropped images for our classification task. So for that, and so here that they are assigning, so for particular means we here we divided into the means, we basically created the labeled data set separately, but that actually there is a labeled data set, but we created separate unlabeled data set, and we are using to assign a label to that particular images, which belongs to that unlabeled data set, it's unlabeled part or something. And we are using those data set for that. And so label is assigned by these labeling functions. The labeling function are basically that our CNN models or CNN models that we do, that ResNet or means if that we are for the continuous, we are if there is a probability of that particular class would be greater than some threshold, then we would assign to that particular class to that particular image kind of thing. And similarly, if the
your voice is so bad, I can't. Are you saying that this labeling function is looking at similarity between an input and a particular class?
Yeah, means there. Hello, am I audible clearly? Hello.
Yeah. What were you saying?
Means that's assigning. Means if there is a particular our model has that it will assign probability in a particular class. That means we have 20 classes, and it will assign the particular probability. What's the probability that it particular image belongs to that class? Hello. Am I clear?
I'm not understanding. Can you repeat once more?
So basically, what these are doing is we're through this we're assigning probabilities of particular classes, like through a model. So say like if you have a data point which is a car, but you pass it when the labeling function of aeroplane uses say model 1, it returns a very low probability because it's not an aeroplane. So your labeling functions are basically giving you these probabilities based on the data points. So
No,
through this, we build
probability is based on what? They are classifiers. They are classifiers. Labeling functions are classifiers.
Sorry, sir.
The whole idea of labeling function is that you should be able to write them cheaply. Are you saying that these labeling functions are classifiers? How? What is this labeling function doing?
Yeah, we're okay. Jay will continue.
Chanakya, please.
Your voice is so bad, I can't understand anything you're saying. So, are these labeling functions classifiers?
Yeah,
Are
so
they doing
we're basically using models to predict these classes, right? So
we was based on pre-trained models. Now these, see,
yeah,
even if this, yeah, so are these coming from a different data set? So see, something has to be cheap, something has to be unsupervised. If you're going to require label data from your target domain, then
yeah.
the whole purpose is defeated, right? The pre-trained model should come from a different domain. That is also fine. Classifier models, pre-trained classifier models could come from a different domain.
So, like, sir, what do you mean by different domain?
See, if you want to do semi-supervised learning, you can't
Yeah.
expect me to give me label data for the target domain and train models and then use them as labeling functions and say, oh, I have an unsupervised learning. That is cheating. That is total cheating. Are you cheating here or are you being fair here? If I say I have data, labeled data from another domain, which I use to train a classifier. Now this classifier may give me, instead of 10 labels, may give 20 labels. But still for my new domain, I don't have to do everything from scratch. Are we having to do from scratch or are we doing everything? No. Are we using something from another domain or are we basically assuming this training data generation required for my target domain? You understand?
So, but like finally, we might have some labeled data set, right? I mean, we will improve our performance using unlabeled data ahead, but with the some labeled data, we can train our models to give pseudo labels some, which can I mean, so basically we can increase the confidence of it and train the model accordingly.
Pseudo label from another domain. Pseudo label from where?
No, pseudo label from the labeled data which we have. Like we have labeled data as well as unlabeled data, right? So the labeled data might be less in number, uh, but we can give some pseudo labels using it and finally increase their confidences using the unlabeled training on the unlabeled data.
So my point is, from where do you train these models? Please, and again, explain to me. I have a target domain. From where do I get the pseudo labeling programs?
Right, so that's what I'm saying. Like with our so say we have a target domain, we have X labeled data set and Y unlabeled data set. So we can train our base, like the 4 base models on the X data set, right?
No, but then the X data set, you're training your models and using those models as labeling functions.
Yeah,
That is
because
not acceptable. That is not acceptable, right?
Yeah, sir, I got your point, but for now we
Might as well use that.
Yeah.
Anyway, you did that, but I'm saying this is not the ideal scenario. You understand?
Yeah. I mean, we should have used something different.
Or you should use, okay, maybe these base models, these base data programs or LFs could be coming from a different
yeah, maybe we can bring it from a
different domain,
yeah,
different
domain.
domain. Could be
That's what
simpler models could be signal processing based, right? Signal processing based
Maybe image
rules.
based also.
Yeah, signal image processing based rules. Right. Okay, algorithms or rules or algorithms, but not deep models. Okay, go ahead. We have to close in next 10 minutes.
We can use list classifications model for the segmentation task or particular kind of things.
Yeah, one model for another model, that's also fine, but it cannot be, I give me training data for the target task, I'll use that to create my labeling functions and use, I mean, that makes no sense, right? I hope that's clear. Yeah. Okay, go ahead.
Yeah.
So, like we assume that the models are pre-trained on the same domain. Like we have, say, in this case, we had it trained on the MS Coco data set already. Like we're just using the pre-trained versions of it to assign labels to the unlabeled data set, and then we use joint learning. Hello.
Okay.
Right.
Hello.
Right. Yeah,
Am
go
I
ahead.
audible, sir?
Yeah.
Yeah, so this was our basic plan. And going ahead, Azim, could you scroll? Yeah, so we train the basic the pickle files are generated with this basically, and then we have our joint learning, which was done for 100 epochs. But yeah, now Azim
Go
would.
ahead. Go ahead.
So, sir, the thing was that we were trying to do this for object classification task, and we were able to run the codes for joint learning and k-learning, but our losses were not converging. It might be because of the labeling functions not working properly, something like that. But we tried to improve the accuracy of these models, but they were like not getting to the suboptimal points. So currently, we have not got good results, which we were hoping that we would find on faster RCN model.
So can you show the results? Can you show the results somewhere?
I mean, we were getting very low accuracies. I mean, I think the cage model was not at all converging. I mean, we were getting very low accuracies for the cage pi.
But do you have any plots? Why have you not alerted anyone? Cage.
I mean, we got accuracies around zero, very close to zero. So we were thinking that something
Did you
is going.
post?
Where?
Did you post on the Git issues?
I mean, I didn't post on the Git issues because we thought we would be able to solve this, but we weren't able to solve this issue. I mean, we were doing it yesterday whole day,
Yeah,
but
so
I don't
like we were.
Yeah, but looks like you have been doing everything last minute now. Isn't that true?
I mean, the thing is, sir,
Yesterday.
we wanted it to work for images because in the previous GitHub, it was done for the text classification, right? So we wanted to do it for the images, and for images, we had to change everything, like the models and every code which was written for text, which we now have to write for image, and the hyperparameters are also now different for the images as compared to text. So might be a problem of hyperparameters which we are using, or maybe something which we are missing out.
Okay, can you at least contributed? Have you contributed to the Spear model? Your changes.
So like we were doing it for image. Lastly it was joint learning was done for the texting. So image thing was not done by anybody. So we were doing it for the image
So that is
classification
okay.
task.
That is okay. I'm saying
Hmm.
that I'm saying. Can you please check this or incorporate this um, into Spear? The
Yeah, we were
Spear code
using
base.
we were using it for
you're
Spear
using.
only. Yeah,
But
we
I'm
were using
saying
Spear.
incorporate your image-based changes. Incorporate your image-based changes into the Spear repository. Just check in it. Make a contribute to the Spear repository for images.
Yeah, sure. We can do it. Once it works, we can change this for the Spear also.
You would have talked to Abhishek, na? He's a TA.
I mean,
so Vishal, just note down. I'm putting in my doc also. You should have contacted Abhishek. He has worked on Spear.
I mean, we didn't knew that we could have talked. At the last moment, I
He's a
talked
TA.
with Abhishek. Okay.
Yeah, please do that. Huh? It's important that you call. Where is your code? Just run us through the code right now.
Just a minute. I need.
You don't have anything more to present, right?
Yeah, I mean, basically, this is what we did. I mean, let me just open the code. I mean, we have done changes on the Spear itself, I guess. Just let me show.
Yeah, please show.
Yeah.
We have the next presentation at 2, right, Vishal?
Yes, sir.
Yeah, Vishal, you can quickly have lunch and come. I'll get started with the next. You can start. Please have lunch and come. Vishal.
It's okay, sir. I had biscuits.
No, don't do that. Just go and have lunch now. Vishal, please go and have lunch.
Yeah, sure.
I think my code is
I'll present.
okay, fine.
So is the screen visible?
Yeah, it is visible, I guess.
Yes, sir. So some changes which we made were just that we included fast RCNN in the feature model process. Like here in the class JN, basically they call a feature model, right? So
I mean, they were using it for logistic integration, and we have added the code for faster CNN also in this.
So basically, in the feature model, we're taking the RCNN as well as an input. So which directs us to creating
an RCNN
the fast RCNN model, which we'll basically use.
Also, you can show the LFS.py for labeling functions, which we have made. Yeah, this LFS.py. So this is our labeling functions which we have written in this.
These were the labeling functions which we made. So.
And also we have made a cons scorer.py. You can show that.
Yeah, in the continuous scorer, we had the prediction, like the probability of the prediction as our continuous scorer.
Okay.
So basically, the probability which we get from using the model.
And we also changed apply.py accordingly for images.
Yeah, in the apply.py, basically here we load accordingly, like load the data set.
Sorry, sir.
Yes.
So where is the code?
Sorry, sir. Like what?
Where have you uploaded the code?
Oh, we have uploaded the code on Moodle, no, Chanu?
Yeah, we've uploaded on Moodle, like the zip folder.
We have uploaded a zip folder, and in that we have changed files in this example of SMS spam accordingly for our image task.
Yeah, there's a sphere folder with some changes that we made. We couldn't put the data pipeline folder because it's too huge. So we just remove that. And also Moodle has 50 MB limitation. So we also did not include the imply loss folder from Sphere because we didn't make any changes from it. So that can be directly taken from the GitHub.
Yeah. Okay. And if required, then Abhishek will reach out to you. So
also, we were thinking that we could have we can extend this in future for the segmentation tasks. Also, I guess.
Yeah, but currently it's only classification, right?
Yeah, I mean we have to first build on
only
classification, and then we can build on segmentation, right? So first the basics classification is done, then we can move on to segmentation also.
Okay. Okay. So, but you should have contacted Abhishek. Please to reach out to him. Huh?
We will reach out after this Viva today
Because
for this.
yeah, this could have been solved easily. It's not a big deal. You cannot be getting 0. Okay, thanks then.
Okay, sir. Thank you, sir.
Thank you, sir.
Anything else you want to present? No, right?
No, sir.
Just this.
So
Yeah,
you
sir.
don't
So
have any
we
results, not a single plot, nothing at all, right?
Yeah, I mean, sir, we were not having converging losses, so that was the issue which we're facing with currently.
Yes, but did you run the text part? Okay, then my question is, did you run the text part?
That SMS spam wala file.
Ah,
I mean, it didn't run it, but the results were already there for in the log file of SMS
okay, but
spam.
see, we don't know.
saw that.
Something could have been wrong. You could have run it locally, right? That's a minimum.
Yeah, I mean, we should have run that SMS spam first for checking that whether it is properly running or
Yeah.
not. Yeah, I got your point. It might be a miniature mistake which we might be doing. I think it would have been solvable if we would have approached Abhishek.
I still feel you have done everything last minute, right? I mean, if you had done it carefully, right?
I mean, sir, we were doing it from last 3 days. I mean, we had to change every work.
3 days is not sufficient. This should have been done. You know, this you should have done
The,
this.
the, the
Much
thing
earlier
was,
project.
the thing was, we changed our project statement at the last moment because we were doing something with LMs and the training for LM time was taking too much. So we were not able to.
But why did you not? But why did you not?
Sir, your voice is not audible.
You could have presented that. You did not present.
So that LLM thing.
Yeah.
So, but that thing is basically we haven't worked upon it. So that the paper which we read in the presentations, which we were going to do the same thing for it. But the thing was that LLM fine tuning takes a lot of time, and so we were not able to move forward with that idea. So we moved on to this cage and joint learning, which because this was feasible for our compute.
Yeah, but you should have picked this up earlier. Anyways, I mean, I, I think some due diligence would have been helpful. Consulting people, you have TAs. Somebody should have you could have asked. Anyways, I think fine. We'll move to the next presentation. Thanks. Yash, can you start? Just talk to Abhishek today, huh?
Okay, sir.
Sure,
Okay,
sir.
Yeah, Yash, can you start? Yes.
Yeah.
Yes, we should start immediately because we have only
Yeah,
till
sorry.
2:30. Yeah, you can start the screen share, please.
So
You're alone.
our
You're
team,
alone.
yeah, like we were team of 3, but they didn't do any work, so that's why.
Acha, so you're a team of 3, but only I should only grade you, right?
Yeah, I think. So uh, our paper was to probabilistic optimization tensor sampling. So in the paper, they used a tensor-based method to update the probability,
Just
and
a second,
then
just a second, just a second. Can you go back again to the top? Okay, so okay, this is what you presented in your seminar also.
yeah,
Hello.
this is the same paper I presented on second.
So, but your project work will be what? You'll be you have
So I've
implemented something.
updated the algorithm. So I updated the algorithm given in this to get like a better results. So
Okay, great. So then why don't you go ahead? Yeah, present it. Yeah.
So do you remember what was in
You can
the
present briefly.
paper, or
You can
should I?
present briefly. You can present briefly.
Okay, fine. So what was that? This is a probability tensor, and here we were selecting capital K multiple instances, and then out of those capital K, we were selecting small k top elements. And then we were updating our probability tensor to minimize the loss function. The loss function was is the probability of these log of probability of these k top items. So essentially, what is happening is just we are giving more probability to k top items. But in the paper, these k capital K and small k top were hyperparameters. So in the paper, so in the algorithm provided in the paper, k top is a hyperparameter whose default value was kept small k by 10. So now we propose a method to find optimal k top by clustering based on values of I. So the intuition behind clustering is that tensor samples from multiple minima, and our goal is to increase the probability of sampling the points which are from global minima. So
sorry,
let's say
tensor samples. You want to pick tensor samples from? Goal to pick
so
tensor
in the
samples
paper they
from?
were just selecting a small k by 10 top elements and maximizing their probability. Now I'm changing this hyperparameter small k top to be such that we can get better results. Is that fine, sir?
K top. What is K and what is K top?
So we are sampling capital K indices, and K top is the like the best small k elements that we want to maximize, their probability. Let me show you in the paper too. So here it's the this small k is k top. So in the algorithm, what was that? To select small k best candidates with indices this and call this set as k, and then update their probability distribution such that their likelihood increases.
The V is give us candidate indices for minimal objective value.
So my work is just on selecting this, choosing this small k. So in the paper, it was a hyperparameter
What
whose
is
value was
the
just
objective
constant.
value? So the objective value is not a black box. This is a black box. Objective value is a black box, is it?
Yeah. So like you're selecting indices, and then black box just gives the values of these indices. That's what.
So we don't have access to the objective value, right?
Yeah, we'll get values this y1 to capital K, and we'll select small k top items. So and then update this probability tensor so that these indices have maximum value. So these indices have more probability. Like let's say y1 and y capital K were best values. So we will update our tensor such that probability of sampling x1 increases and xk increases. That is what we are doing. So
so the goal is to find the top k and then go back and update the update the tensor.
yeah.
Only for those top k indices. What will you update in for those top indices?
So that is defined by this likelihood function. So this is the likelihood function, and we'll change our parameters of a tensor. So like a tensor has some parameters which were like let me show you. Yeah, so these tensors are going to update the value in the tensor. So we are representing a n1 cross n till nd matrix or tensor, you can say, by this in tensor train format. So we are going to change the parameters of tensor train format to get such that their probability increases.
I see. So but then the top k items, you will go and boost their values. What will you do? what will you do? So we
Yeah.
compute black box values for the k multi indices, and what will you do for the top
Mm.
k items?
So we change our this tensor parameters such that their probability increases, which is done by this minimizing this likelihood function. So maximizing this likelihood function. So we'll change the theta parameters of a tensor such that this is maximized. Where xsi is just the small top elements.
Theta parameters. So that likelihood of selecting any select okay, फिर से मैं एक बार देखूंगा.
So let me explain you by this
Put the
graph.
corresponding
So
function
let
values. Values y1 is f1, fx1, y2 is fx2, yk is fxk. Select kxk best candidate to the indices S. The minimum objective value yj is equal to y and j. Take the probability distribution p theta to increase the likelihood that so you want the selected candidates likelihood to be updated.
So let's say like these blue points are our sampled from theta out. These blue points. Now we want to increase the probability of sampling these points, because at the end what we want is to just sample this point with probability 1 always. This is the global minima point with probability 1. So now what they were doing is they were just selecting some small k top elements. Their intuition was that all of those will belong in this region only. But now what I'm doing is I'm clustering based on that. So I'm like dividing these values in two clusters such that all these points are in one cluster and all the other points are in another cluster, and then update the probability of all these points. So so in their algorithm, it might happen that this element also come in the small k top best elements, and it will increase the probability of sampling this point too. But we don't want that. We just want to increase the probability of sampling these points, which lie around.
So what I
global
don't
minimum.
understand, okay, maybe so you're saying the top k items should correspond exactly this global minimum points, right? That's assumption. Assumption is top k will be exactly this global minimum. How do you guarantee that? How do you guarantee that these top k are exactly the global minimum?
So I am not guaranteeing that this is what was done in the paper and it works. So like.
So you're saying no, but you're saying select k bus candidate.
Yeah, so they were just selecting top 10% of points. Can I? Yeah. Sorry, can you say that again?
So I don't understand this. Select k best candidates with indices S from with a minimal objective value. Yj less than equal to y capital J. So how do you get the? So you're saying the algorithm will learn to pick the top k to correspond to the global minimum?
Yeah. So my algorithm So in their algorithm, just k was constant, small k was constant. Now in my algorithm, at every iteration, it will choose the best small k so that it can update the tensor even better.
In their algorithm, the value of k was constant, or the examples corresponding to those k were constant?
Value of small k were constant. Examples will change, right? Based
Yeah,
on.
obviously. But you're saying in your case, your k value itself will change.
Yeah. So at every iteration, I'm not just selecting the same number of best candidate. I'm selecting all those points that lie in global minimums.
Okay, maybe proceed. But I still don't understand what is the goal. The goal is to learn the more learn so that you'll end up picking the global minimum to be the top k, or the goal is given that assuming that the k will correspond to the global minimum, modify the probability tensor accordingly. So that which of the two? Option one, which is estimate your top k so that it corresponds to the global minimum. That's what the whole algorithm will eventually learn to do. Second is no, the algorithm assuming that some oracle gives you the top k that correspond to the global minimum, will your algorithm will change the probability tensor. Which of the two you are doing?
Yeah. So in their algorithm, they are not assuming anything. So let me just clear that what intuition is that, let's say these blue points are sampled. Now they're sampling just small k elements, small k best elements. They're sorting based on values and selecting small k best element. So it might happen that they will select these points and this point, let's say, which I'm pointing towards the right. And now they'll update the tensor to maximize the sampling probability of all these points. So it might happen that this point also comes in the small k best elements. It might happen.
So so assumption in some sense is that the top k correspond to the roughly to the global minimum. No, that's an assumption.
Yeah, but without that assumption too, we can do better. So let's say like in one iteration, it selects this point. Now, but in second iteration, it will select because so it's converging more to global minimum. So it will select points from these points only in the next iteration. But it's the loss of one iteration, you can say. Let's say it just maximize the probability of this and these points. Now, it will select points from this and this minimas. And then in the next iteration, it will select points only from this minima. That's the intuition of their algorithm.
Okay, so no, can you repeat? You're saying that assumption I said is the top k roughly corresponds to global minimum, and you're saying that's not required. It learns to pick the top k to be what? What were you saying just now?
Yeah, I'm just saying exactly that. Like it isn't necessary to so that all the small k points are from global minima, but it will learn eventually, right? Because
how that I don't understand. You're saying because it has probability tensor. Okay, go ahead.
So wait, let me just explain how it will learn. So let's say the small k best elements include this point and these point. Now in the next iteration, it will sample more from this and these points. So in the next iteration, hope is that the small k best element lie only in this, because we are increasing the probability of sampling from this, right? So it will have more samples from this, even
yeah,
from
but
this also. But
I'm saying roughly. Again, I'm using the word roughly. The assumption is the top k roughly corresponds to the global minimum, at least initially. Otherwise, it will drift away, Baba. Okay, I got what you're saying. I think you're not getting what I'm saying, but I hope now we can proceed. Go ahead. At least initialization, if it's wrong, it will just drift away. That's my point. Understand? Na? Initialization, if it's wrong, it will drift away.
That is true. If the initial are all from local minima, then it will just keep sampling from extract and keep sampling from local.
Go ahead.
Wait, so my objective function.
Now you move to what you have done, your experiments. Yeah, that's why presentation is always helpful. Anyways, go ahead. Hmm.
So like this were the comparison over iterations and the minimum value found through the prods their algorithm and our algorithm.
What is the difference between prods and prods updated?
Updated is my algorithm where I'm choosing k-top to be to minimize.
What is the objective function again you use for k-top?
Where did it go? Can I?
Okay, just bring it up. I'll be back.
Yeah, wait, I had it on here. So wait, so like the objective function was to just select the k-top such that it divides them into two cluster and like minimize. So just clustering of the
Yes,
points.
I think sir is not there. Can you wait?
What?
I'm not sure sir is there. Sir will be right back. So can you just wait for 1 minute?
Yeah, sure. Sir.
Hey, you stop screen sharing, is it?
The TA has said that you were gone. Wait, let me.
No. I just said I'll be back. I wanted to know what is what is updated.
So in the every point the k, the value of k is changed instead of prods. In the prods algorithm, the k was fixed to be capital K by 10, and in our algorithms it is changing so that to capture only global minimum prods.
But how are you determining? That is fine. How are you determining the k? So I mean, I'm not understanding what is prods updated doing specifically.
Yeah, wait. I didn't put the objective function of k. Wait, let me.
Hey, Baba, that is your thing, na? I mean, how am I supposed to know?
Yeah, sure.
You're saying that value of k is obtained dynamically, right?
Yeah, so value of k is changing.
How?
So let me show you in the code what's the.
So I'm assuming this is 100% your contribution, 0 from your two teammates, right?
Yeah.
Okay. Seminar, was it equal? Seminar?
No, in seminar 2 also.
You didn't say that.
I made the whole. I made the whole presentation.
So seminar, their contribution was how much?
0, you can say, like.
Acha. You're saying 100% yours, 0 to them, huh?
Yeah. Seminar also.
Yeah, you have to be very pretty sure. Yeah, I'm fine because they were there in the stage with you. You never told me. I have right. Vishak, I had kept on announcing students should let us know if, but you didn't let us know. How am I supposed to know, right? Go ahead.
So, like, here for I in range 1 to k, I'm just this objective is this, and I'm just selecting best try if the objective is less than objective previous. So what is this? Is S1 is just the like summation from the distance. So summation of the distance from the cluster mean, and S2 is the summation of the distance from mean of cluster 2, and the sum of there. And
Sorry.
so in the clustering, what we do is we minimize the we find the best mean and minimize the distance from a cluster's points to cluster mean, and then do it for both the clusters.
So you do clustering to find the value of k.
Yeah. So
what are you doing? You're clustering the points
based on the value of y. So let's so these were the points. These points will be in same cluster, and these other points will be in other cluster. So this is what I'm doing. Right?
Yeah, and then how are you updating the value of k? I'm not still understanding. What is the exact formula for updating the value of k? Here, you're saying proportional to the number of points in that cluster. So if the previous cluster had fewer points, and now this cluster has more points.
So yeah, just depending on the number of points in a cluster. So if in one sampling it has 20 points, we'll choose k to be 20. If that the next sampling it becomes 30, we'll choose 30. So
okay, so it's very, very vague. I mean, you're saying it's all in that. It's all in that black. Yes. Yeah, I should have latex. At least you should latex it now. First of all, you may not be sure what you have written. What you have implemented is what you intended to, right? That's a problem. You have intended to do something, but you have probably implemented something else. So always good that you do things very systematically. Huh? Yes. The projects are opportunities for you to become systematic.
So I can submit the reported updated report if you give me some today's time.
Okay, so I'm going to assume it's only you who have done. No marks to other two for seminar as well as. Okay, can I say 95% yours for seminar and 5% for them?
So what was like I made the whole presentation in the end. Like just before the presentation, they said, "How can we remain silent?" And then I said to them, like, "It's okay. You can present the last few slides." So this is what happened in the presentation. So
yeah, but
and the project was done by me only. No
the project obviously they are not even turned up. I can't give them any marks. Okay, fine, got it. I'll take care. Thanks. Please update the presentation. Update the.
Of course. I'll update the present report.
Yeah, I mean, have at least make it complete now because it took so much effort for me to understand what you have done. I got an idea that you're using clustering and somewhere proportional to the clustering, size, you're updating k. That hint I've got. But if you document your exact formula, you'll know whether what you implemented is what you intended to. Okay? That's a summary. Thanks. Then we'll move to the next presentation. Thanks. Yes.
Thank you, sir.
Yeah, update the report. Ninad, you can start the presentation, please. Ninad, can you please start the presentation? Hello, Ninad. Vishak, am I audible? Ninad is not responding.
Yes, sir, you are audible.
We should start the next one. We have only 1 minute left. Okay. We are doing well on time now, Vishak. I think this pace is correct, na?
We are doing well on time. One other group messaged me. They were supposed to give presentation at 4:30, but he said he's currently doing some internship or something. Is it possible to swap with another group? But none of the groups are ready to swap.
Yeah, that is their problem. We can't help it now. Internship, I mean, he cannot be on internship before course grades. No, he has to be there. No, he has to be there then. If nobody's ready to swap, it's not our problem. Grading is not yet over. Internships cannot just take precedence. Okay, Vishak. I mean, this was announced long back. They should be available. Internship cannot take precedence over course. Vishak, please tell them to be there. Huh? If no one else changes, they should be there. That's it. Period. Or whoever was supposed to be at 6:30, they can stop. That's also fine. Now 6:30 guys got allocated only now, na?
Yeah,
Somebody
I asked them and they said they are currently outside and they cannot
we have
exchange with.
Yeah, Nina, please start presentation. So,
Hello?
Yeah, Nina, please start presentation.
Hello, sir. No,
Yeah.
Sir,
Yeah,
actually, I'm traveling right now. There might be some network issues. Anup will be presenting. He's joining like in 1
No,
minute.
we have to start immediately. Yeah. So, Vishak, the last presentation is scheduled at what, 7 p.m. or 6:30 p.m.?
6:30 p.m.
7 p.m. will be done, right?
Yeah, 7 p.m. will be done.
Yeah, please go ahead. Please go ahead, Anup. We need to start. Anup, please start the presentation. We are running out of time here.
Yes. I've shared the screen. Is the screen visible?
Yeah, it's visible.
Yes. Only three of you. Where is Khare? Lyric Khare.
Sir, actually, Lyric is on a flight right now. So his flight got delayed apparently. So that is why he's not able to come.
Is the contribution equal from all three or?
Yes, sir. Contribution is equal.
Yes, sir. Yeah. So unfortunately, like his flight was at.
Go ahead. Go ahead.
Okay, sir. So, as we present, so our project is about LLM fine tuning. So we have used the method called KTO. So this is basically a new method that the authors have developed, which takes in only single preference. So rather than two pairs, rather than a pair and preference, it only takes these four values as the input. And we basically tried to implement this particular model on a very on a smaller LLM the Pythia 1.4b, and tried to see how the the LLM file to come up with the results. So basically, our motivation for doing this was because firstly the preferences data which is there, it's very limited. So if you see and getting for any kind of a task, getting the preference data, let's say for medical task or any other instruction fine tuning task, getting that particular data is kind of very expensive. But we have a lot of data in the form of
binary output or a score output. Let's say like from any kind of forum, or any kind of forum, we can get a lot of such data which has scores or upvotes, like let's say Reddit, which we can take the upvotes as scores, for example. So we have a lot abundant of these data, and the second motivation for choosing the model of Python was the resource constraints which we had. Like we didn't have a lot of GPU resources, so we chose the like smaller model of Python and tried how the fine tuning will how.
So there's
So
no
we
presentation, is it? There's no presentation, is it?
so actually we weren't aware that we had to do a presentation, so we
Because
didn't
most of the
prepare.
teams have done. Yeah, okay.
Okay,
I mean,
sorry.
see, the way you're walking through a report, it's not that convenient for me.
Yeah. Sir, we're extremely sorry. We were not aware that we had to make a presentation. Okay. So the objective is
So
like
the only motivation is preferences data is limited. That's the only motivation.
yeah. Apart from not just that, from the paper which we had go through, and we had also presented. So the other advantage of KTO over other methods like PPO or DPO is also that even if there is abundance of, let's say, desirable data. So basically, KTO calls classifies the data as like desirable data or undesirable data, that is chosen or rejected. So even if the abundance of like the chosen data is very less compared to the undesirable data or rejected data, still the performance of the model is quite good, better compared to like models like DPO or PPO. That's also other advantage. So we'll start with the
Yes, sir.
data set.
And
Yeah.
yeah, and in the paper they have proposed some results that in their method KTO they outperform various other LLMs who have been fine tuned using DPO with much less amount of training data, and also that class imbalance of desirable undesirable. So yeah, these are the motivations.
Okay.
Yeah. So we start with the data set which they have like basically used the SHP standard human preference data by Stanford, and so we also tried to and also they've used the HHR and open assistant conversation data set. These are the data sets which they had used on Python, like Python 30B and 7B or 30B, etc. models. So we also tried to use the same particular data set. But then we defined a custom data loader for the project, because they haven't mentioned the data loader for getting from us, like from not from preference data, or like from not from the paired data. So we had to define a data loader for the unpaired data set, which we had used. Uh,
You have to define data loader for what?
for the unpaid data set. Yeah.
Unpaid.
Sir, yes, sir. Actually, the data sets which they are using, like SHP and Anthropic HH, they are primarily preference-based data sets. So either they are taking preference like values, or they are taking unpreference values, which they are kind of separating from the preferences. So if one response is preferred over the other, that will become desirable, and the other will become undesirable. But there is no straight pipeline for a data set who directly have unpaired preferences. So our like data set which we used, Anup, can you just go a little above? Yes, sir. This LLM feedback data set. This is this is like a preference data set which we are using. So to use this data set, we defined a custom data loader. So this was not done in the paper. This is what we tried.
So like these particular data set only has like the scores of the given criteria which they had defined. to basically evaluate the feedbacks. So there is only the score value. So it's not a preference or paired data here. So for using this particular data set, we have defined this data loader which takes the unpaired data, and then we have set a threshold value. So basically this score threshold value, if you could see, and that is what is said. If the basically if the score which they had defined is below a particular below the score threshold value, then we'll take it as rejected or undesirable, and if it is above and equal, we'll take it as chosen.
Now, are you saying this is where a data loader was required to remove filter? You're saying data loader was required to filter out? Is that what you're saying? Hello?
Sir, filter out what?
Yeah.
For filtering out undesirable values.
No, sir, we are not actually
Yeah.
filtering out undesirable values. We are just passing them in a different
Yeah.
format. So if the score if the score is less than the threshold, it will go in as undesirable, like rejected thing, but the model will still learn from it. And if it's the score is greater than the threshold, then it will go as a desirable input.
So basically, this wasn't something which was defined earlier.
So
And
it's kind of like
yeah.
binary, where like the desirable has a +1 reward and the undesirable has a -1 reward. So the model will learn from using the reward as an anchor.
Mm-hmm. So the model will use. Can you repeat this last point again? Can you repeat this last point again?
So like the desirable / undesirable aspect is similar to like giving a reward of +1 for the
Mm-hmm.
desirable input. The model will get a reward of +1, and if the input is undesirable, the model will get a reward of -1. So it will learn from that reward. So it will learn to steer towards the desirable
Acha. Of course.
outcome. Yes.
Passing input in a different format in the sense. Okay, just
Yes. Yes.
Yeah.
for marking undesirable. For marking
So
undesirable.
actually in the preferences one, they were directly passing the log logits, the difference of the log logits of the preference inputs, right? So that could directly go in the loss function. But for this, it wasn't as straightforward. So we just made like a few changes in the data loader, and defined a custom function. And yeah, we made those changes.
Okay.
Hello. So, Ninad, there is already a KTO trainer available in Hugging Face, right? So, what do you mean you made a custom trainer?
No, I did not say we made a custom trainer. We made a custom data loader.
Data loader.
Yeah.
Not a
We made the score unary trainer, which we have, like if you can see the above picture. So that just takes one single input with a score value, and if that score is above the threshold, we are returning the example. Like the example is like the prompt, the generation of the prompt, and whether each generation is desirable or undesirable. That way.
Okay. Carry.
Yeah. So like.
So Vishak, you should take interest in this, no? This Vishak, you should have certain interest to you, right?
Yeah, I'm.
Okay. Go ahead. You guys are you guys are doing your BTech 4th year?
Yes.
Yes,
Okay,
sir.
but would you be interested in pursuing this into paper submission? After, obviously not immediately, but in a few months.
Sir, actually, both of us have finished our 4th year, so that would mean continuing in the summers, like a project.
Like, are you proposing to like do it as a project later?
Right. Not project, as paper. Yeah, project in the sense. But Vishak will talk to you. Okay, Vishak will talk to you.
Yeah, I'll do it.
Yeah, go ahead. Go ahead.
Okay.
Yeah.
Okay.
So after that, like we then tried to then do the training of like Pythia 1.4b, but then given the resource constraint, we had to do like drop down the all the epochs and the number of samples which are getting generated to a very lower value, like the, let's say like only two values of eval examples and n examples because of the resource constraint. We are using only Google Colab GPU, the T4 GPU. Yeah.
But some students had asked me compute and I gave them also. So whoever asked, I tried to give. Nobody. I mean, if it, I didn't publicly put out because then it wasn't clear.
So like you like very initially told that don't like for particularly for LLM fine tuning you won't like really get
Yes, sir. Actually, I think we had initially come to talk to you, like
yeah,
just
and
after you
we did
announced
come.
project, and that time you had said that giving resources will not be available. So,
No,
Like
like,
for
I think
LLM.
the understanding was that you'll always come back after you do your initial homework on the kind of slightly non-LLM setting. That's what everyone does, right? You don't start with LLMs always. You always start with non-LLM setting and then move to LLMs. If it's a analytical kind of work, so you can always. Actually, one or two students asked, and I tried to give them whatever I could. But anyways,
Like
go ahead.
we actually needed GPU from very starting because we first like wanted to try like need to run the code which they had provided and then shift to our data set and like define data rulers and then like train on our particular data set. So we actually needed it from the start. Okay.
Okay, no problem. So instead of Pythia, owing to
So we tried Llama 7B. We initially tried Llama and all, but yeah, basically it also tries to load two models. The one is the preference model, and one is which is getting trained, so which is getting fine tuned. So that is why it takes up a lot of memory also.
Okay.
So yeah, we'll, we'll define the size. So this is like training loss and compared to the
which model? Sorry, I'm still not clear. Which model is this training loss for?
Pythia 1.
sir, yeah, Pythia 1.4b and
4B.
2.8b. Because like the other models, we did not have enough GPU memory to fit. So this was on the custom data, the LLM feedback data set.
Okay.
Yeah. So yeah, so we tried. So we observed that the training loss did actually drop down, but the evaluation loss was like comparatively like similar because again the number of epochs which we were able to train it on, and then we also compared the KL divergence with the preference model, and also the rewards which were which further chosen for during the training and also during the evaluation. And this is also the GPU utilization, which was almost like 100% overall. And so,
Sir, actually, since we were doing it on Colab, we also tried quantization of the models first. Like we were seeing whether we can quantize some of the bigger 7 billion models. But we faced into some dependency issues, like some libraries like flash attention and all that do not work on, do not work properly on Colab's GPUs, and like they were creating problems with quantization. So that is why we also had to scrap that. We mentioned it in a report also.
Okay.
so like to come up with the final conclusion, like so we also showed the generation rate.
I see. You said scrap attention. What is that?
Flash attention. So
No,
basically, it's the model for
flash attention.
flash.
But flash attention does not work on Colab.
No, sir. It only works
so
on Turing GPUs, and like Collapse GPU was not one of them. So like we had to we got it to work somehow, but it was like using an older version of flash attention, so that created
Oh,
little problems with quantization also.
I see, I see.
Yes, sir. So like in conclusions, we could see like the training loss was decreasing, but the evaluation loss was kind of hovering around the same point. I think majorly because the size of the model is not very large. So it also like we made some inferences also, and those were hallucinating a little bit since the models the size of the models are small. Uh, yeah, but we could see like the output was definitely a little better than just the pre-trained, like the
No,
pre-trained Pythia models.
so KTO, acha, but you're saying you could not comparison against DPO could not be made, right?
Yes, sir, because of resource constraints.
Oh, acha.
but like we did compare the responses with the initial the pre-trained models, just the pre-trained model. Finally, also to conclude, like we like with the paper, the paper results and the results which we found was basically that the KTO model is KTO optimization is like very much good for like larger models with like Llama 30B and all, but it doesn't make a lot of lot of basically improvement for like smaller models for like 1.4P and all these models. Even it was there in the paper it's also, and we kind of saw it in our project as well.
Yes, sir. Actually, in the paper, they the metric they used was called win rate, where they use another model like GPT-4 to assess to compare the inputs. So we tried doing that, but like the same thing, we could not make that working on Colab. Yeah. So I mean, since the training was also not very long, so it would not have been a fruitful comparison anyway.
Comparison against DPO and PPO, you're saying?
Yeah, like
Yes, sir.
DPO
Between
and
DPO,
KTO.
PPO, between KTO, DPO, and KTO, and just the pre-trained model.
Yeah.
So what was the last point? I missed it.
Sir, they have
So like
used a separate model like GPT-4 to compare the outputs between like the KTO optimized model and just the pre-trained model, or KTO optimized and DPO optimized, like to compare. And the metric they used was called win rate. So that is essentially the quality. They assess some kind of quality of generation through GPT-4 as like the
I see, I see.
comparative model.
Can you show that data set once again?
so we also this is the data. We have the link below in the references also.
Yeah, can you show that?
Yeah, this is the link.
I don't think so that taggle page is visible, Anup.
So that is then share. I guess, yeah, now it is visible.
Okay.
Hello.
Yeah.
Yeah, so yeah, this is it. So this is the data set.
So this data set also has like several other evaluations. Like one evaluation is from a human evaluator, like which gives the description of how the model has performed. So that was not really useful to us, like in the experiment we were using. So yeah, we did not use that. We used the score which is given, the response, and of course the prompt.
So here the original three score description is better than 5 score description, something like that.
Sorry, can you repeat?
So the difference between 3 score description and 5 score description in the column.
No, actually, like those are like different evaluators, basically.
So Vishak, your question's answered?
Yes, sir.
Okay. So then I think you tried presenting your code. Where is your code? It's part of the, I'm just looking at Moodle.
Yeah, in the report, that actually included the GitHub link as well as the collab link in this report itself, in the starting itself. So yeah, this is the code. So this is the GitHub link where we have made the changes in the code, and this is the collab which we run. So yeah, this was the collab which we ran. Also the MongoDB results are also there. And we could observe the MongoDB results as well.
Okay, thanks. And I think we'll move to the next presentation. Anup, Ninad, please work with. So Vishal,
Okay.
I think they
Thank you,
can.
sir.
No, Vivek, just wait before you leave. I feel
Yes, sir. Yes, sir.
you can actually work with Vishak. Vishak, just the attribution problem will be interesting here, na? Because I mean the Adobe collaboration, we could do something. Compute we can make available there for this attribution. But no, using KTO, can you actually work with Anup Nina, because they have actually spent a lot of time. So maybe they should be able to come up with a.
Yeah, we can. I will contact.
Yes, sir. We'll like have a talk
Yes, sir.
with Vishak, right?
Yeah.
Yeah, Vishak only now, because Vishak, you already tried DPO. If you can bring in diversity, right, through KTO. Actually, what is the KTO objective? Can you just show once more the KTO objective? We have maybe 2 minutes left.
Yeah, we have it in the report.
Allows to utility instead of maximizing the log likelihood. Exactly. So this need a binary signal of whether not. This is good now, Vishak, for attribution.
Yes, sir.
Okay, so